Yes, sure.
Welcome to the afternoon scientific session. We're going to have 3 talks before coffee and then 3 talks after. And so the first talk this afternoon will be Professor Alice Sinatra from École Normale Supérieure, the Laboratoire Castres Bruxelles. She's been a collaborator with the Institute of Physics for many years, especially with Professor Witkowska. She's researched many ambitious topics in quantum mechanics, ultra-cold atoms, and quantum metrology. Professor Sinatra got her PhD at the University of Milan in 1997, and then she's been at INS, I think, most of the time since then. So I'll leave the floor to you.
Thank you, Piotr. So first, I would like to thank you very much. It's really a great honor for me to be here, and also very interesting to learn about all the amazing activities going on in the Institute of Physics, Polish Academy of Sciences. So I'm going to tell you about atomic sensors and their quantum limit. Here is the plan of my talk. So I'm going to, introduce some very basic atomic sensors, and I can show you that they are very precise and that they present a fundamental quantum limit. And it is with this quantum limit that we want to play, introducing these quantum technologies of spin squeeze states that were already mentioned briefly by Emilia Witkowska. And then I will give you an application of this spin squeeze state, telling you about a recent work that we have done about sensing an extended field with them. Okay, so let's take a very simple system, quantum system with 2 levels. We all know that if we put the system in one of the 2 energy levels, this is a stationary state, and the properties of the system will not evolve in time. While if we put our system in a superposition of these 2 energy states, this is, of course, not a stationary state, and the system will evolve with a frequency which is given by this energy difference. Instead of a 2-level system, you can also take, of course, which is equivalent, a spin 1/2 in a magnetic field. And so if you put this spin 1/2, you have the magnetic field, we represent it in the block sphere here. Does it work? Yeah. So if the magnetic field is vertical, and if we put the spin 1/2 in the horizontal plane, orthogonally to the magnetic field, we know that it will precess with the Larmor frequency, which is given by the energy difference between the 2 states. And with this very simple principle, one can build very precise atomic sensors. So there is a first case, simple case. If our 2-level system is isolated from the rest of the world, then, for example, if it is an atom of a given atomic species, and we select a transition, this energy difference will be given by nature. And so it's a standard, a very, very nice standard for the frequency. And this is what happens, for example, for atomic clocks. We have heard this morning the very nice talk of a professor von Klitzing, and it was introduced. This time unit is taken from a transition of cesium atoms, hyperfine transitions, such that the second is defined as a certain number of cycles of this given transition. And so for the atomic clocks based on microwave transitions, like the cesium or rubidium atomic fountains, the best one with very cold atoms, one can get relative precision on the relative uncertainty rather on the frequency, which is 10 to the minus 16 by averaging in time. And then there is now even more precise generation of clocks based on optical transition, where they can reach 10 to the minus 18. So this is incredibly precise sensors. The second case is the case in which the system, the two-level system, is not isolated, but is in an external field which affects the energy difference. For example, a magnetic field. And in this case, the system can be used to measure this external field. And here I want to put just an extreme example for magnetometry using nuclear spins of helium-3 in their ground state, even at room temperature. Due to the very long coherence time of these spins, actually they can measure very small magnetic fields corresponding to 10 to the minus 4 femtotesla by integrating in 24 hours, so very precise magnetometry. Okay, but they are very precise sensor, but they do have some intrinsic quantum noise, and I would like to explain you what it is. It is also very simple. So let us consider first a single spin 1/2 here. I represent it on the Bloch sphere. So, and I put this spin along the direction x of the Bloch sphere. So if I measure the direction x, I will always find 1/2 with no noise. But if I measure in another direction, if I measure, for example, the direction y, we know that it will be 0 on average, like on the picture, but when I measure, it will be plus 1/2 or minus 1/2. So there will be a huge quantum noise. Actually, there will be a standard deviation of 1/2. If we now have not one, but n independent spins, I can sum them to form what we call a collective spin. It's just the sum of the individual spin that I will represent on the Bloch sphere. It's a big Bloch sphere of radius n/2. And then if each of the small spins points x, then also the collective spin points on the direction x. And when I will measure Sx, I will find n/2. But when I will measure orthogonally to the mean spin, I will have some quantum noise. And if the atoms are independent, here, this width is square root n. Sorry, I skipped I was here. So this width, this quantum noise, is a square root n, because the atoms are independent, so it's the variances who sum up. And so for the standard deviation, I get a square root of n. And so you see that this uncertainty transversely to the mean spin gives an uncertainty on the angular position of the spin. And so we will find this uncertainty when we try to use this as a sensor, measuring the precession frequency. And indeed, the atomic clocks, the fountains that I was mentioning before, they are sensitive, they work at the quantum limit, that is, they are sensitive to these quantum fluctuations. So which scale? So the angular uncertainty scales like the width, which is square root n here, divided by the length, that is n. So they scale like 1 over square root n. And also, if I want to measure a frequency, this will depend on how long I precess. So the final uncertainty on the frequency will be 1 over square root n and 1 over time of precession. Okay, now what we can do with this, we can, this is a sort of simple quantum technology, we can reduce this uncertainty here, distributing it differently among the two components orthogonal to the mean spin. So for independent atom, we have this situation that I just described, but we can create quantum correlations among the atoms, such that the uncertainties in one direction, here, the direction y, are reduced, so that I can better point the direction of the spin. I reduce the angular uncertainty on the position of the spin. And this so holds only for correlated atoms. And the consequence will be that when I want to measure the precessing phase, the uncertainty of the phase will be the 1 over square root of n that I have for independent atom, but reduced by a factor that we call psi here, which is smaller than 1, which we call the spin squeezing parameter. So spin squeezing, it means that, in fact, we squeeze the fluctuations of a collective spin by correlating the atoms. So here in this page, I would like to give you some ideas. Are these spin squeeze state useful, what they could be useful for, and what are the main challenges? So first of all, we have seen that when we have independent atoms, so no spin squeezing, the noise that we have in this angular position, the uncertainty, scales as 1 over square root of n, 1 of t. So this means that for a very, very large system, this quantum noise will be very small and not very important. It could become important if we go to small numbers of atoms. For example, if we go towards miniaturized sensors, then at some point, or if we cannot integrate during a very, very long time, at some point we will stump into quantum noise and we can get advantage from the quantum correlations. So this is a way, this is one case for miniaturized sensor, and the other case would be if we want to be really as precise as possible. For example, some fundamental physics experiments we have heard this morning about the variation of fundamental constants by spectroscopy. So in that case, we want to have the most precise measurements, the largest atom number, and on the top of this, we want to add the quantum gain to be even more precise. Then we can say that there have been already, as I will tell in the next slide, some experimental demonstration of spin squeezing. And we can say that this will go probably from the lab to the application, to technology, under some conditions. One condition would be, for example, that it's not too complicated to obtain them. If this quantum gain comes somehow easily, it will be used. Or it could be that it's absolutely necessary. And somehow a nice story for us doing spin squeezing is to look at what happened with the squeeze states of light that were widely studied in the 80s and that are finally now used in the interferometers for the gravitational wave detections. What are the challenges in general for all these quantum technologies, and this doesn't make exception? The challenges come from the decoherence. That is, we want to make a quantum state with quantum correlation, but this has to be protected from decoherence. First of all, in order to get an advantage, we want the decoherence to be low such that the limitation of my sensor is already the quantum limit. Otherwise, I will not gain by changing the quantum limit. And the second thing, I want to be able to prepare a quantum state that will survive the time of the measurement. If these conditions are there, then we can get some gain. And so I would like here to give you a few experiments that already, examples of some experiments that already were showing spin squeezing. And there are two major ways of how to do it, this operation of correlating the atoms. So the first one is to obtain somehow in the system an effective Hamiltonian which acts like the collective spin component SZ, which is the number difference of atoms in upper state or lower state, squared. So it's a nonlinear operation, somehow like a Kerr effect for the matter field that will squeeze the spin. And this can be done in different ways. For example, in Bose-Einstein condensate with interactions, atom-atom interactions, in fact. Also putting the atoms in a cavity and letting all the atoms interact with a common mode of the cavity. And in this way, what was achieved was, for example, a gain of the order of 10 on the variance, orthogonally to the mean spin, for ensemble of atoms like 1,000 or 100 for condensates, and 10,000, up to 10,000 for systems in the cavity. There are also new methods that Emilia Witkowska was mentioning that are very important, that will work in optical lattices for optical clocks, although they were not yet implemented, but they will, I'm sure. And then another class of method is by measurement. So by if you can measure by a quantum non-demolition measurement one component orthogonally to the mean spin, it's a way to prepare a spin squeeze state. And recently, much progress was done, and up to a factor 100 of gain on the variance was obtained in the lab in this way. And also an important thing is long-lived squeeze state that were created in a metrologic environment, a squeeze state that can live for up to 1 second. Okay, now in this second part of the talk, I would like to give you, this is theory and application that we imagine of these squeeze states to sense an extended field. For example, a magnetic field or another field. So we imagine the following situation. We have a regular arrangement of single atoms. It could be, for example, in an optical lattice, 1 atom per site. And then at each side, I have some field. Actually, it could be a continuous field. Here we take a field, for example, the direction is vertical, but the amplitude can vary from side to side. And the principle is that I prepare my spin 1/2 initially all along the direction x with this state. They are not correlated, they point x. And then locally, they sense the field, so they do a small Larmor precession proportionally to their field. So by measuring the rotation, I can get to the field I want to measure. And mathematically, I can describe this phase encoding by some operation with the generators, which are the z component of the spin 1/2. As we have said just before, when I go to measure this small precession, since they are single atoms, I stamp into the quantum noise. That is, if my spin 1/2 points x here, and I want to here, and I measure along y, I have this standard deviation of 1/2, sorry, which is there. Of course, I can improve on the quantum noise here by repeating the measurement, because if I repeat many times the measurement, the signal will go proportionally to the number of measurements, that here is mu, but the noise only like square root of mu. So I will gain in signal to noise as 1 over the square root of the number of the measurement. But I can also correlate the atoms with spin squeezing, and this is what I want to do. So if I want to take advantage of the correlations among the atoms, I don't have to measure locally each atom, but I have to measure all the atoms, some collective quantity. And the first thing that I can show you here is that if I prepare, so imagine that initially all my spins point x like this, they are not correlated. Then, and this is the initial state, which is here. Then I act with my squeezing, that is a sz square operation here. And then the round here becomes a sort of banana, this way, that I can orientate by doing single atom operation. I orientate it vertically, so that is sensitive to the position. And then I imprint my phases to the system like this. And then I measure just one component of the collective spin. That is, I do a collective measurement. I go through all the atoms, and I measure the SY component of the collective spin. So it's easy to see that this component of the collective spin will be sensitive to some quantity, theta, which is the spatial average of all the parameters. Because each small y, which SY for each atom will sense the local field, and I sum all of them, so I get the sum of all the fields. So this is a way in which I can feel the spatial average of all my parameters, or of my local fields. And if my state is squeezed, that is, if the fluctuations in SY are reduced in the squeezed state, I can get these spatial averages with some quantum advantage with respect to independent atom. That is, the uncertainty on the spatial average will be 1 over square root n, and then there will be this parameter xi, spin squeezing parameter, smaller than 1. Okay, so this is nice. I can get this spatial average. But in fact, I don't want only the spatial average. I want every field. I want all of them. And so I will have to have n independent linear combinations of the parameters. The spatial average is a particular combination with all the coefficients plus, 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 plus. And so what is the way out? The way out is to consider, as I said, n independent combination, and we consider combinations with coefficients which are plus or minus 1. And these coefficients can be, in fact, introduced in experiments by making spin flips before and after the imprinting of the phase. Before and after the imprinting of the phase, we make a pi spin flip. Sorry. And the effect of this is to put a minus sign in front of a given parameter. And so, in this way, when we now measure the collective component Sy, it will give access to some linear combination, which is not the average, but which has some minus sign here. And so to formalize this a bit, in fact, the combination that we want to measure are the coefficients of the so-called Walsh-Hadamard transform. That is, the matrix which connects the initial parameters to the combination is a matrix made of +1 and -1 that I represented here, such that these rows, normalized, are the Walsh functions that I represent here. So the one which is plus, 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 plus is the one which gives the spatial average. And then I have one which is plus and then minus, and then I have more and more switches. And this function can be used as a basis for a discrete Fourier transform. And so here you understand also that what you can do, of course, you can measure all the combinations and then use the inverse transform to find all the coefficients. But you could also measure less combinations, like doing a truncated Fourier transform, and then reconstruct your coefficients. And with this technique, we have shown that you can get the same quantum gain for each parameter, that is to measure each local parameter, and the quantum gain is given by the usual spin squeezing parameter that you have initially prepared in your system. Now I will just give you a few examples of applications. So in this simulation, we do as if we were experimentalists. We have a field which has 3 components. For the 3 components, we took 3 sinus forms, simply dephased. They are the black curve here. So for the x component is sine. For the y is sine plus pi over 2, and then pi plus pi for the z. And then we apply this protocol. That is, we prepare a squeeze state. We do the pi pulses to select one combination. We measure the combination with some number of repetition of measurements. We measured all the 8 combinations, because here there are only 8 sites, 8 atoms. And we reconstruct the signals. And an important thing is that even though the field has 3 components, by choosing the direction, the initial direction of the atoms and the direction of the measurement of the component that I measure, I can select one by one these components, so that I can measure the 3 components subsequently. And here you see the results. So you have the error bars here in green for the case of uncorrelated atoms, the so-called coherent spin state. And in yellow, you have some improvement here when you use the squeeze state. You have smaller error bars. And in fact, by squeezing like we have done it with this SZ square Hamiltonian, there is a feature that is the more atom you have, the larger the gain. So here the gain is not very large because we only have 8 atoms. But I'm going to show you now an example with more atoms. So in this case, we have n, it is the number of atoms and also the number of signals, equal 512 square. So this is the number of parameters of phases that I want to write into my system, I have the same number of phases and same number of atoms. And this is a scalar field, which is coded in the color code of the image. So the original signal is this figure here. And then I measure some linear combination corresponding to the different Welch functions. And here, we do not measure all of them, which would be like 10 to the 5. We measure, instead of measuring 512 square coefficients, we only measure 64 square coefficients. And we reconstruct the image with the coherent state. This is the first image. And with the squeeze state. This is the second one. Sorry, I don't master this, sorry, this story. Okay, and this is with the spin squeeze state. And you see that there is a nice improvement. And in the lower figure here, what we did is that we prepare a squeeze state that is not perfect. That is, during the preparation of the squeeze state, there is some dephasing noise described by this master equation. There is the part producing the squeezing, is the first Hamiltonian part here, and then there is some collective dephasing processes going on so that the state is not perfectly squeezed. And so the quantum gain in this case is only about a factor of 10. But you see that still there is a nice improvement. And then last, we also made a test with a small number, a relatively smaller number of atoms, so about 1,032 times 32. So our signal now we take a detail here that we amplify here. This is the original signal. And this is the reconstruction with an imperfect squeeze state in presence of dephasing and with a coherent speed state for comparison. Thank you very much for your attention, and I can take some questions, if any.
Thank you very much, Lisa. So we can have some questions. Is there a question over there? From, wow, okay.
So to actually implement this protocol, you need to have like single particle resolution, yes, to have this flip, or no?
Yes, you need to have a single particle control to flip, not to measure, but to flip.
To flip. Is it possible to do it now?
Of course, it's possible. Okay. Yeah, that is. They can do it in many platforms. They can do it in cavities, in tweezers, and also in separated BEC.
But I was thinking about the optical lattice. So is it possible to like just flip spin in a well-given lattice site, not touching others? Or?
I think that also in optical lattices they could in these microscopes. I am not sure, but some first experiments are going on with separated BEC.
Okay.
Okay, thank you. Are there any other questions at this stage? If not, let's thank Professor Sinatra again.
Thank you.
Thank you for keeping in time as well. And let me introduce our next speaker. It's Professor Maciej Lewenstein from ICFO in Barcelona. He's a famous theoretical physicist with many ties to our institute, which I think he will talk about, judging by the title. So he did his PhD upstairs at the Center for Theoretical Physics and also with Professor Fritz Harke at Essen University. And I guess you traveled to a number of places. I think you had a faculty position in Hanover, and before that you were with Roy Glauber in the US and other places until you finally made it to Barcelona. And Professor Lewenstein is a recipient of many national and international prizes. I might mention the Willis Lamb Award in 2016 and the prize from the Foundation for Polish Physics in 2011. And I will give the floor to you. Thank you very much.
Thank you very much for the introduction, and also it's a great honor to be here. So when I got the invitation from the director, it reminded me that in 2016 I got the doctorate honoris causa from University of Warsaw, and I gave a talk there. It works or not? Yeah. So it was, the talk that I gave there was a physicist in a shadow university. So I thought I take the same, I'm lazy, so I take the same slides, just change the University of Warsaw to IFPAN, and that's it. And this is what I did. I changed it only a little, really. So does it work? Here. Okay, so but I changed the title a little. So it's IFPAN and me, very many intersections in various places and on various levels. I always start my slides with all these grants that are financing our research of quantum optics theory group at ICFO. And because of many logos, there are many people in the group. It is a huge group, but still we have been able to go beyond 30 now. So it's starting to be under control. Okay, the outline is that I will indeed, a little like Emilia in her talk, this will be a memory talk, or if you wish, a homage to Institute of Physics. And I will talk about my links with Institute of Physics and joint projects and give examples like Emilia was giving. So I will start to talk about quantum optics, and each of the parts will be organized in this way that there will be some short introduction and example of research and gallery of photos. So the second part will be matter in intense laser fields. The third part will not be there because there is no time. This is about complex systems and neural networks and all this stuff. Ultra-cold matter and quantum many-body physics and quantum information. So let's start with quantum optics and quantum electrodynamics. So indeed, this is a slide from my doctorate honoris causa. I was explaining how it happened that I came. Actually, I should say my most of career in Polish Academy of Science was related to Center of Theoretical Physics, but it was here in this place, as Professor Iwo Biancki-Wirula explained in the morning. So when we were finishing diplomas, me and my best friend Marek, we wanted to do mathematical physics, but the dean of the department said no more good students for Professor Morin. There is too many mathematical physicists. He forbidden that. That's why we wanted to do something about quantum field theory. So we went to Zakład of Quantum Electrodynamics and Statistical Physics of Iwo Biały-Białynicki. And we both started to our diploma there, talked to Kazimierz Zążewski and Krzysztof Wódkiewicz, who told us that quantum optics is applied quantum electrodynamics. So it was kind of, okay, quantum field theory, finally. And I started my diploma with Kazik and Marek with Krzysztof Wódkiewicz. That was, of course, at the university. Then, after the diploma, I worked 1 year at the university, but then IBB, I don't know how to say, and Zążewski moved to the newly formed center, at that time, Zakład Fizyki Teoretycznej, and they proposed me to go there. Very important role in my life played Łukasz Turski, who was also a faculty member there, because he has defended me from going to the army twice, I guess. If not there, I wouldn't be here, I'm sure. Okay, so these are the papers that I just collected from those times that are related to quantum optics. So my first paper actually is with the, this is very difficult. I agree with Alice. Can I go back here? Okay, so my first paper, no, it doesn't allow. My first paper was with Jan Mostowski. I remind you that at those days, Kazik had very complicated problems with the eyes, and in fact, very much quite large part of both of my diploma and then beginning of PhD, he spent with the doctors. And Mostowski was actually play a role of my co-supervisor, I could say. And very early, many of early papers are with Mostowski. He influenced, evidently, my early career very strong. another thing that I point you out here is something that Professor Bianconi didn't tell, but the students that we had in the Center for Theoretical Physics were students of the Institute of Physics, because we didn't have at that time the possibility of giving the doctorates. Moreover, my doctorate from SN, I had to nostrificate in Poland. And where did I nostrificate? At Institute of Physics P.A.S, with some protest from Professor Zofia Białęcka-Birula, because she pointed out that I didn't do the exam on Marxist philosophy, but it was nostrificated anyway. So my alma mater, actually, formally in Poland, is IFPAN. Okay, so I want to talk about two papers I want to mention of Jan Grochmalicki, who again, he was student formally in IFPAN. He did his diploma with Jan Mostowski, if I remember well, and then he was my first PhD student. We were working at that time on, it was very fashionable to work on quantum jumps. So we were working on some exotic models of quantum jumps. So this was open systems, so two-level atoms interacting with some reservoir, which was not so trivial in a sense. So you see, these are reservoirs which have density of states in the continuum which have some shape. And therefore the physics becomes a little non-Markovian, since these are all Lorentz shapes. This is Fano profile, this is something even simpler, the simple Fano profile. Then the dynamics at the very end is Markovian, but for more degrees of freedom than just the two-level atom. And why do I talk about it? We wrote two papers about it. The second one was even in cavities, or cavities or waveguides, where the reservoir can become to have power law density of states and power law decays. Why do I say? Because this thematics of, or this subject of quantum jumps is coming back now very intensively in fundamentals of quantum mechanics and not only. And the reason is that normally, well, first of all, you can measure these quantum jumps very precisely. So you can measure the quantum trajectories, essentially. You can trap individual atom, and you can measure quantum trajectory from individual atom, ion, or whatever. Second, you can measure not only quantum jumps, but you can also make a measurement of this on another unraveling of this open system dynamics, which is the Wiener process. So it's a quantum Brownian motion, if you wish, which was proposed by Gisin and Percival many years ago, but which is corresponds to measurements we're using sophisticated homodyne techniques and things like that. But in principle, it's measurable. Not so precisely, but it's measurable. And now, you can do the following thing. You measure some physical observable for one single quantum trajectory, in this picture or in this picture. Now you make quantum mechanical average, and then you average over all trajectories. Of course, the result will be the same, because these are two unravelings of the same master equation. But you, in the laboratory, you can do other things. You can take a quantum mechanical average of some observable corresponding to single trajectory, square it before averaging over trajectories. And then the result will be surprising, because the result will be that the average over trajectories of this squared quantity will be different for different unraveling. So it's not true that the density matrix describes all the time single time averages of the system. This is not true here. And that's something that is related also to measurement-induced phase transition, hot subject nowadays. So it's quite, this experience that I got with Grochmalicki here is quite important now. Okay, this is the gallery, as I said. I couldn't find photos of neither of Grochmalicki or Kuklinski, but you see here many people. Adam Kujawski, who was also taking care a lot of me, and he got involved me in editions of the first two volumes of the quantum optics proceedings of our famous conference. Władek Żakowicz, Roger Trautmann, and Jan Mostowski again. What the hell is this? I don't know. Okay, many people here whom you know. Unfortunately, many of those who are not more with us. Fritz Hacker, Joe Taus, Roy Glauber. Okay, let's go to the second subject. So this is about matter-intense laser fields and the so-called strong field approximation. So the story was that the first person that influenced me in that sense was both Kazik, but Professor Zofia Białynicka-Birula, who wrote a very influential paper on above threshold ionization. It inspired Joe Eberly, who published the same results in PRL because he was better marketing person, or is even. Kazik spent some time in Trieste in ICTP and brought some preprints of Louis Davidovich, where Louis were working exactly on the interpretation of the Keldysh approximation of tunneling processes, and that inspired me to start work on this process. Again, Mostowski played a very important role. We first wrote something about the above threshold ionization. Well, essentially at that time we were working only about above threshold ionization and electron scattering and collective effects in multi-electron ionization, but not about harmonics. But it was a very good school for me, at least, to understand what the tunneling is in this dynamical situation. Here is Joe. Okay, these are the papers from those times, and in particular, probably the important one is this one, which was part of my habilitation, which was done where? In the Institute of Physics of Polish Academy of Science in the end of '86. So this is, of course, going to be about this year Nobel Prize, which was rewarded 2 weeks ago. And the story is that this was rewarded, as you know, for generation of ultra-short light pulses, which are so-called attosecond pulses. So the pioneer of this is obtained within the process, which is called high harmonic generation, which I will explain now. And pioneer of this process was Anne Laurier, who did these experiments in 1988. The other pioneer was Charles Rhodes, but he's passed away also. And but Anne was the first who observed the so-called plateau in the spectrum. I will explain it in the second. I was, funny enough, already as a docent here, and already 1 year before getting a professorship from Lech Wałęsa, I was her postdoc in Saclay for 6 months because the only money that were available were for postdoc. But anyway, she has contaminated me with the high harmonics generation. So what is high harmonics? What you do is you take a super short you take a ultra short laser pulse and you focus it on some target, for instance, atoms, which go from the atomic jet here, and then you look what's going out, in particular on photons that go out. And these are these high harmonics. You can measure the spectrum of them by using some intelligent optics in XUV and things like that. The spectrum that you get typically has the following sense. The low harmonics fall down like in the perturbation theory, more or less. And the, so them. It's like Russian TV, I would say, when I was small. So there is a plateau then, which is evidently non-perturbative, and there is a very rapid cutoff. But you can go to very, very high harmonics here, in principle. So these are the typical spectra. Now, if you take discrete harmonics like this, and you go to the time domain, then what you get is attosecond pulse train. So this is what Pier Agostini realized, and this is for what he has got the Nobel Prize. Attosecond pulse train. Why? Because the harmonics in different elements of the spectrum are phase locked. So they come with the same phase. If you add e to the I q times omega times t from q equal, I don't know, 5 to 25, then you obtain a sequence of pulses which go periodically with half a period actually here because only odd harmonics contribute, but pulses of the duration which is laser period divided by the number of harmonics that come into this packet, so to say, that you consider. And Krauss was more interested in going to this continuous type of harmonics in the cutoff so that he could observe single attosecond pulses. And this was his main achievement for which he obtained the Nobel. The mechanism is the famous simple man model or three-step model, which goes back to Ken Kullander and Paul Corkum, who of course feel themselves probably a great losers of the recent Nobel Prize, because although the Nobel Prize had the logic was to give it to the experimental people only, and to pioneer, Anne-Loulier, and to those who were first observation of attosecond. So it's very logical. And there is a third paper, which is a so-called Lewenstein model, which has been celebrated in 2019 as the most cited paper of Physical Review A. It has now in Google over nearly 5,000 citations, and in Web of Science 3.5. And it is still cited very, very intensively, and I will explain why. So the three-step model was a semi-classical model in which Kullander and Corkum said, well, first of all, there is single active electron. The lasers are strong, but not so strong that they destroy everything. There is single active electron in the ground state. So what happens, it feels the oscillating electric field of the laser. So it's like a linear potential in which it is. These oscillations are slow in comparison to the electron binding energy. Okay, they are 10 times slower or something like that. So when the electric field is huge, electron may tunnel out from the nucleus, and essentially it feels free. It doesn't have any constraints. It's accelerated in the laser field, first in the direction in which it went, but then goes back because the laser field oscillates, and then it can recombine to the ground state again. And in this process of recombination, it produces harmonics. And how big harmonics it can produce? Well, it depends on the amount of kinetic energy it can gain by being accelerated here in the laser field. This is a classical mechanics. I can solve it analytically. It's just free electron in electric field oscillating. And it turns out that the amount of energy that it can gain is 3.2 roughly of the so-called ponderomotive energy, which is average kinetic energy of electron oscillating in the sinusoidal electric field. Okay. And this is what this is the reason for how they got this Nobel Prize. I'm just saying that this whole area, when we have written the first paper with Anne and Misha Ivanov and sent to PRL, George Bazbaz said, no, this area is completely finished. We are not going to publish any paper, any physical letter on high harmonic generation anymore. And we published it as a rapid communication to PRA, finally. And the big paper, the one that I was talking about in Peace Revey. But this whole area has new revivals. For instance, this is a revival. Normally, in those theories, you always describe a laser electric field as a classical number because it's so strong that quantum fluctuations can be neglected. But since few years, we are trying to do theory and experiments in which we see the quantum, so to say, nature of these fields. And this is, in particular, this nature physics, in which the idea is that you put the coherent state on a target. It turns out that if the depletion of the target is not too large, the coherent state remains coherent but is shifted because of interaction. Then my colleague Paris Salas from Crete diminishes the amplitude of this of this coherent state to, say, average 10 photons. Here there are 10 to 8, and here is 10 or 20. And then at the same time, he conditions this state on production of harmonics. So that the resulting outgoing post-selected state is this shifted coherent minus projector on the original coherent, okay? And obviously this is a superposition of two coherent states, and therefore it's a Schrödinger cat. And indeed they have measured this. It's a little more complicated, and we have written 10 pages. It's like a gold mine, this new subject. So this is the results of measurement. If you just don't do nothing, you put coherent state, and you have now 10 photons in the system on average. So you can measure tomographically Wigner function of the state, and this is what Paris-Salas did. If nothing happens, it's just a Gaussian. But if you put interaction with the atomic gas, you measure a very beautiful Schrödinger cat with taking into account all the imperfections of the measurements with negative parts, etc. I mean, we have just, for the occasion of the celebration of Professor Ivo Białyński-Birura, we wrote a short article with my student, Philip Stammer, dedicated to Ivo, about quantum optics as applied quantum electrodynamics is back in town, because now it's really quantum electrodynamics. This is the gallery again. Important role in those collaborations played Mariusz Gajda from IFPAN. There are 3 Nobels here. With Anne, I have, I don't know, 25 papers maybe. Pierre Agostini and Ferenc Krauss. There is Paul Korkum also, and Ken Kullander, with whom I also had the honor to collaborate. Okay, let's go to ultra-cold matter. Somebody tells me how much time I have. I can skip the last part. Anyway, so in '93, I went to Gila in Boulder as a visiting fellow and started to work on Bose-Einstein condensation. And I continued to work on this attoscience because I finished this paper that I just mentioned. But I have to run a BEC seminar together with theorists and experimentalists like Eric Cornell, Karl Wyman, Peter Zoller, and Ignacio Siraco was visiting there. So it was a fantastic time. Then I went to Paris and started to work with another Nobel, Claude Cohen-Tanergy, and Jean Dalibard and Yvan Castin. And then I went to Hanover, where again Bose-Einstein condensation was the top thing. Again, several papers were written with the people from Institute of Physics of Polish Academy of Science. I mentioned here this one with Mariusz and with Ertmer and with Łukasz Dobrek, who was my student in Hanover, if I remember well. So this is the idea is at that time everybody wanted to generate vortices in the BEC. So the idea is you take a absorption plate, which is like this. So it has, the white is small absorption, and then you go around and you have here big absorption and a jump, obviously, because you cannot have quasi-jump, actually, because you cannot have really singular things. And now you put the light through it and shine it on the Bose-Einstein condensate. What happens is that this light should be strong and short pulse. So it will act, all the dynamics of the condensate is not important during this pulse action. So what will happen is it acts like exponent to the I times duration of the pulse times the potential, which is proportional to this absorption plate. So you imprint a phase on the wave function of the condensate. And this, indeed, the condensate adjusts itself. Of course, there are some instabilities and blah, blah, blah. But at some moment, depending on how strong it is and how long you apply, you adjust it to having one vortex or 2 vortices and things like that. We also discussed in this paper how to detect these vortices using interference of condensate with the vortex with condensate without vortex. Quantum simulators, I think everybody knows what it is. There are many interesting phenomena, and they are very often difficult to, they can be quantum or classical, I don't even mind, but they are difficult to be understand with the classical computer, so why not use a simpler, better controllable quantum system to simulate them? And this goes back to Feynman and his termed as quantum simulator. A typical example would be superconductivity. Everybody knows here what is superconductivity, especially in IFPAN. So superconductors conduct strong currents without losses. They exhibit this pushing of magnetic field outside of them due to Meissner-Ochsenfeld effect. Unfortunately, they only exist in low temperatures, so even high TC superconductors are in low temperatures. So we would like to understand the process better in order to design maybe materials that are superconducting in room temperatures. Applications are obvious. First of all, you can get a Nobel Prize, and many people have. Even Ig Nobel Prize was given for improbable research. Usually I have a movie here, but there is no time. So André Geim, the Nobel Prize for Graphene, and the prominent Sir Michael Berry got Ig Nobel, improbable research, for using superconducting magnets to levitate a frog. You can also levitate the trains, and these are the real applications in many countries, including China, of course. Some of us believe that there exists a simple model that captures the phenomenon of TC superconductivity, which is the Hubbard model. Even this simple model is very hard to simulate, so why not try to mimic it with atoms? Simple Hubbard model, this is the idea. The electrons, which have spin up or down, and therefore two colors, red and blue, can tunnel from one side to another, or can interact. But of course, two blue electrons cannot be in the same site because they cannot be in the same state due to Pauli principle. If you have more bands, maybe. But if you are restricted to the lowest band, not. And this is described by the simple Hamiltonian, which has been shown even today several times. It's not, we don't want to understand it, but it's so short formula. Nevertheless, it's very complex to solve numerically. And this you can do with cold atoms in principle. So we make this optical lattice, but by making standing waves of atoms. Standing waves create standing electric fields, oscillating but standing. And electric fields shift the energy of the atoms due to the Stark effect. Linear Stark effect oscillate like hell, averages to 0, but quadratic Stark effect oscillate like cosine squared, so averages to 1/2 and creates a potential. And again, we have a lot of papers. Here I started to maybe collaboration with Institute of Physics relatively late. 2011 is maybe the first paper. Yeah, I would say. But there are many papers. In particular, there is this review of non-standard Hubbard model in optical lattices, where both Mariusz and Tomek participated, which is about extended Hubbard models, but not only extended. So not only that interactions, density go from next neighbors, next neighbors, etc., but also that there are exotic tunneling processes like pair tunneling or like density-assisted tunneling and things like that, which might play a very important role in different models of superconductivity. So these models are important, and so in this review, in particular, discuss examples of this. This is a Bose-Hubbard model extended, so with next nearest interactions, and this is the dipolar Hubbard model. So with interactions, we go like 1/3 in 2D, and that lead to all these exotic phases at different feelings, like checkerboards or different type of checkerboards, etc. We wrote a book about it, quantum simulators, with Anna and with Veronika Finger, and there is a lot of papers from IFPAN which are cited in this book. And this is the gallery. Mariusz, of course, Tomek, who is working on his similarity to Arnold Schwarzenegger, and a lot of Polish people, but particular these two, right? So Michał and Emilia. And Julia, who was also working on the board of Institute for some time. And finally, quantum information. I have some time or not? Okay, so quantum information I entered very early because I was working in neural networks in the 80s, and then in 94 I wrote a paper about quantum perceptron. So I had already the idea that machine learning should become quantum and things like that. This paper nobody read, but now people are sometimes reading it. Anyway, I started to work with Anna, who contaminated me with the obsession of solving separability problems, of deciding which states are quantum correlated or entangled and which are not. And then I started to work with Ignacio Cirac, who was probably my closest remote collaborator at that time. But I was also working with very many other people. But some of them are here, Jarek, Remik, etc., etc. So these are also Indians, which played a very important role, and Tony Yassin from ICFO. The papers that I quote as examples here are very recent, actually, and one is with Emilia, both are actually with Emilia. I will talk about the first one because it's related, first of all, to the Nobel Prize of the last year for Alain Aspect, John Clauser, and Anton Zeilinger. Second is related to what Emilia was telling us and what also Alice Sinatra was telling us about all these models of one axis twisting. This is a PRL where we generate many-body Bell correlations. So the Hamiltonian is this square of, so we have in this case we talk about the two-component Bose system in which you can treat two components as spin components. You're using Schwinger construction. You can build angular momentum to global angular momentum operators, and Hamiltonian is proportional to JZ squared. So it really causes one axis twisting. And what we do in this paper is that, of course, everybody looked in this problem on the squeezing parameter, which for the short times becomes very small, and therefore you have a lot of entanglement. These lines here mean that how deep is this entanglement. K depth of entanglement means that at least K particles have to be genuinely correlated, and K depth of Bell correlation is the same, that at least K particles have to be genuinely. So the lower you are, but the important thing that we calculate here is a kind of squeezing non-parameter which depends on higher order correlation functions. It's not easy to be measured, but in the experiments with, let's say, 8, 10 ions or atoms, Rydberg atoms or so on, it is measurable, and then it can serve to characterize the states, the Bell correlations in the states in this one-axis squeezing dynamics for the times longer, because squeezing as such goes to small values and then vanishes. And this is the gallery, which is mostly Polish and Indian. And again, there are people from here, Julia, Michał, Emilia, and our friend Tomek, reminding Arnold Schwarzenegger. Unfortunately, again, several people here are not with us anymore. Krzysztof Wódkiewicz, Andrzej Kosakowski, and I guess this is it. I have 5 minutes or not? No. I will.
Something to wrap up.
So the conclusions are very simple. Okay, we have this program of doing a connection between the quantum statistics and music. So I wrote a book which is on the internet if somebody is interested on avant-garde music. free improvisation in particular. But I really have a postdoc in the group, which is a composer, and we're trying to really sonify the quantum stochastic processes, somehow transfer them to the sounds. No? So in particular, I don't know, the spontaneous emission of a single trapped atom. Can we hear anti-bunching? And things like that. Of course, this is absolutely not canonical, the way she transforms the things to the sounds, but it's a lot. We learn a lot on that, and we gain a lot on that. So we had a concert at the Sonar Festival in Barcelona in 2021, and last in June we had the conference Quantum Sounds, where several people from all over the world came, including IBM, because they tried to do something with quantum computers, and that maybe this is the most interesting application of quantum computers, actually. And she wrote this, but I don't know if it will work. So this is actually a sonification of this dynamics of the Wigner function of the Schrödinger cat. And staccato is supposed to symbolize the negative parts of the Wigner function. And this was the premiere in Latvia because she has good friends in Latvia. I think this is it.
Thank you very much, Maciej. Is there a quick question somebody wants to ask? Or if not, I think we'll ask the next speaker to come forward, Georges Boulon, please. And while we're preparing, let's thank Maciej Lewenstein for his talk. So let me introduce our next speaker, Georges Boulon from the Université de Lyon. So he did his PhD in 1970 at the University of Lyon. He's a fellow of the Optical Society of America, author of well over 500 scientific articles. He's got many outstanding contributions to optical materials and topics related to luminescence. Yes. He's a long-time collaborator with Professor Suchodzki here at the Institute. And he has the title of Doctor Honoris Causa in several universities, among them the University of Wrocław in Poland, which I'll mention because it's close by. So I'll give the floor to you. Thank you very much.
Thank you, sir, for this very kind presentation. I would like to say, first of all, that I am very honored to be there. Thank you so much, Professor Wisniak, for inviting me. Thank you so much, Andrzej Chorowski, to invited me here also. I have a very strong cooperation with different Polish labs since 1983. I was nominated head of my lab after Mrs. Groom in Lyon, and my first Polish worker who asked to come in Lyon was Michel Malinowski from your institute, and after I had some very strong cooperation with Andrzej Chorowski, also with University of Gdańsk, with Marek Greenberg, and later on with the University of Wrocław, the Academy of Science, with Professor Streck, with the University of Wrocław, with Janina Lejanzewicz, and since 15 years, my strongest collaboration is with Małgorzata Guzik at the University of Wrocław. So I am very lucky to have such Polish collaboration because I met very competent Polish researcher and we had very friendship relationship. It's very nice. Thank you so much. So I would like to speak today on research of efficient fast scintillator, mainly on the role of cerium 4+ ion. Cerium 3+ is used as dopant in a lot of oxides, and this materials are used for fast scintillator. I will give you two examples. You see, with cerium. First of all, the evidence and the XANES characterization of cerium of cerium 4+ in cerium magnesium co-doped garnet crystals, and the second one with glass, with cerium doped, you see, fluoro-oxide glass. We will see why I use these two examples. I work at ILM, you see, Institute Light Matter at the University of Lyon. You see the campus of Lyon, and our lab is there anyway. You see, this institute has 300 members, you see, 80 PhD. We have some publication, obviously. You will see on this website more details on our activities. The summary of my talk will be the following one. First of all, introduction of scintillator, and after I will speak on rare earth 3+ doped cubic garnet. We will select this garnet, so-called GHGG, for gadolinium, aluminium, gallium oxide. We will try to understand the scintillation mechanism, and we will confirm cerium 4+, because it is a question. Is it really the intervention of cerium 4+ in these garnets? And we will use XANES measurement by using synchrotron at ESRF in Grenoble. And I will say also a few words on this last result on cerium doped glass for potential UV scintillator. You see, this is the introduction with scintillator. They are liquid scintillator. This is the example in Japan at Kamiokande to detect neutrino. Organic solid with commercial plastic in Saint-Gobain in France. And inorganic solid. I am involved in inorganic solid. The most new is probably lead tungstate. Before it was BGO, bismuth germanate. And now it is lead tungstate at CERN. And also, new ones are cerium doped orthosilicate and garnet. About scintillator, we have to know that there is no direct detector of gamma rays, and we need the fast scintillator materials to convert high energy radiation to UV or visible radiation. I remember these relationships on the probability of the transition, where it is the inverse of tau, the lifetime of the transition of the excited state. And you see that it depends on wavelength, and shorter wavelength emissions gives a faster response. This is the principle of scintillator for detection of X-ray and ionizing radiation. You see, from gamma ray, X-ray, we transform into visible light. So from one photon in very high energy, we have n photon of very much lower energy, and so we have to count this high energy photon. We need fast response, absolutely, to detect all these photons. And so the speed of scintillation process depends on the duration of the output light pulse. It is determined by the luminescence decay time of the emission center, and also by the timing characteristic of the transport stage. It is obvious. So this is to summarize these stages of the scintillation processes between conduction band, between valence band and conduction band. After absorption of a high energy photon, we have some thermalization in 10 - 10 seconds, recombinations on emitting center of trap in the materials, and if we have a dopant, we have to trap it on this dopant, and so we will try to detect, depending on the lifetime of the excited state of this dopant, we will try to detect the photon. So the application are very well known. I don't insist in medical application, high energy physics, security check, unbroken analysis, nuclear energy, radon detection, geology, and so on. This, the example I would like to give quickly is the medical imaging technique, so-called PET, positron emission tomography, and how to detect photons, c'est-à-dire gamma ray, because the system detects pairs of gamma rays emitted indirectly by a positron emitting radioligand. Most commonly, it is fluorine 18. Lifetime is 110 minutes, which is introduced into the body on a biologically active molecular called the radioactive tracer. And so we have positron-electron interaction, emission, you see, of gamma rays. And if we turn around the body for different position, you see, we will get exactly where is coming the active center. So now I will speak about the direction of our research on the 4F 5D transition of rare earth 3+ doped crystals. These 4F 5D transition are parity allowed electric dipole transitions, and thus have larger oscillator strengths and shorter radiative lifetime than the more familiar 4F transition of a rare earth 3+. And so we choose cerium 3+. It is the first rare earth ion, very sensitive to absorption and giving a strong luminescence emission, doped crystal glasses for fast scintillator. This is the configuration of the cerium atom, the cerium 3+ with 4F1 configuration. And so you have absorption from 4F level to 5D, and so emission from 5D to 4F. We have systematically two bands in emission, in UV and visible. You see, always two bands, and these two levels are separated by about 2000 wave number. Which kind of materials we are used? Today, we commercialize scintillator like orthosilicate, so-called GSO, gadolinium silicate, LSO, lutetium silicate, and a mixture, LiSO, for lutetium yttrium silicate. There are great research and development effort brought several new single crystals, normally pyrosilicate and chloride and bromide of lanthanums. But I would like to speak on a project I was involved with a Japanese colleague at the University Tohoku in Sendai, Japan, on LUYAG, you see, lutetium aluminium garnet oxide, and GAGG, gadolinium aluminium gallium oxide. So I will also give some few words about another collaboration I have with Japan, but with Osaka, with Institute of Laser Engineering of Osaka, on this glass APLF doped with praseodymium, cerium, and neodymium. We will see why. So I want to give an important previous work, which was developed by my colleague at the National School of Chemistry of Paris. You see, it was to put out the evidence and consequence of cerium 4+ in LiSO, doped with cerium calcium, and LiSO doped with cerium magnesium single crystals for medical imaging application. the role of cerium 4+ and the help of calcium 2+ or magnesium 2+. There are favorable effects, it is easy to understand, of calcium and magnesium 2+ co-doping, because we have the creation of stable cerium 4+ center in this garnet structure, like it is mentioned here, gadolinium plus gadolinium, then 3+, then magnesium 2+ plus cerium 4+. So such center create another fast radiative recombination pathway working in parallel with the classical mechanism based on the stable cerium 3+ center. We can say that skipping the first hole trapping stage avoids the delays in hole trapping prior to electron trapping. It results in acceleration of the decay and suppressions of low components. You see, the sequential charge trapping scheme suggests that cerium 3+ can be seen as a pre-prepared cerium ready to trap a free electron. Cerium 4+ center traps such excited electron directly from the conduction band, leading to excited 3+ and their radiative recombination. So in the garnets, we have similar interpretation, similar assignments. I speak on garnet, they are very well known, like YAG, you see, and other garnet single crystals. They are used for phosphor. For some cerium 3+ doped YAG is very well known. You use them for lighting at home or in your car. We mixed the blue light with the yellow luminescence light of these crystals. They are using for persistent phosphor, for luminescence thermometry. They are very well used for laser when praseodymium, they are doped with praseodymium, neodymium, holmium, erbium, thulium, ytterbium. There are a lot of used rare earth doped garnets, and also for magneto-optics host. So this work is done in cooperation with Institut NEL, with ESRF, European Synchrotron Radiation Facility in Grenoble, because I know very well, and I work with Géraldine Dantel and Denis Testemal. My colleague in Lyon is Yannick Guyot, and in Poland, our co-worker is Małgorzata Guzik from Faculty of Chemistry at the University of Wrocław. And in Japan, this is a work with Institute for Material Research, IMR, at Tohoku University with Kurosawa, Kameda, and Professor Yoshikawa. You see, I don't insist about paper which were published. It was a few years of research with this cerium 3+ doped yttrium, gadolinium, gallium, aluminum oxide. Many huge paper, many research work, and I wanted to mention it. They use two kinds of technique to grow crystals. The first of all, very convenient technique, so-called micro pooling dome technique, you see. We use it in Lyon also, because I spend a lot of time with this laboratoire since 1987. We have very strong cooperation since a long time. And you see, we have done such a paper with Yoshikawa, Martin Nicol from Prague, and Professor Fukuda to point out this technique and to get very quickly, you see, in 5-10 hours, one single crystals, and it is very inconvenient. It is enough to study all characterization. But we also are using Czochralski method, you know, obviously, this technique in Poland, to grow bulk crystal, but it is much more expensive, and it takes longer time, you see, 1 week, 10 days for one crystals. But when we have determine by micropooling dome technique all parameters of a crystal. We can grow it by Shogrelsky and to get a big bulky crystal. You see, the work has been done by using a lot of crystals was allowing to determine what is the role of gadolinium, of gallium, with different gallium concentration, and to know more about these materials. This is an example of a single crystal obtained by Shogrelsky technique, you see. It is 1% cerium 3+ doped gadolinium, aluminum, gallium oxide. We got exactly with my colleague Karedine Lebou at the Université Lyon. We got the same kind of single crystal also. So it was just to summarize the property. And we got excellent light yield, you see, of about 56,000 photons by MEV, but I wanted to say that this is the value exceeding by 40% the best cerium 3+ doped LISO from the group of the National Chemistry in Paris. So, however, it is possible to find a better solution. And the better solution is obtained with co-doping this GHG garnet by magnesium 2+. I summarize here two absorption spectrum. You see, one is only, the blue one is only doped with cerium, and the other one is co-doped with cerium and magnesium. So you have, first of all, 4F 5D transition. I mentioned them here in this energy level diagram. Gadolinium absorption line, they are very well known also, but you see when we co-dopt with magnesium 2+, we have another broad band. It is a charge transfer band absorption. Charge transfer band from the oxygen orbitals to the valence band to the cerium orbital of cerium. This is cerium 4+. So we have always cerium 4+ and cerium 3+, you see, but from this absorption spectra, we don't know the ratio cerium 3+, cerium 4+. It has to be confirmed, first of all. We have to be sure it's really the cerium 4+, and also it has to be quantified. And so I add the radioluminescent spectra, the cerium 3+, only doped with cerium, GHG only doped with cerium 3+, and co-doped with cerium 3+ and magnesium 2+. This is excitation by X-ray. You see the emission intensity of cerium band, it is in the yellow, it is very well known. You saw the color in the previous slide. So you see that the emission intensity of cerium 3+ band decreased by magnesium 2+ co-doping. And when we are studying decay curves, we see that when we co-dopt, we got decay times, which is most notably accelerated by magnesium 2+ co-doping, and the light output decrease as confirmed by the emission spectra. So it is really in the sense where we are looking faster and faster scintillator in the nanoseconds scale. So this is a promising scintillator for application, which require fast timing resolution and high light yield such as PIT, as I show you. And you see they are grown by micro-PD, by Shogrelsky technique. We got short decay of around 40 nanoseconds and a second composite, 142 nanoseconds, but it performs better than cerium calcium co-doped GHGG crystals. You see, what is the scintillation mechanisms? We have to remind that the presence of cerium 4+ in cerium 3+ doped single crystals has always been a big issue. So how to probe it? VM is this work is to clarify the role of cerium 4+ in this compound. And so what are the mechanisms? I try to summarize quickly here the different steps. You have cerium 3+ plus all when you are absorption of X-ray excitation, you have all trapping, you see, cerium 3+ plus all plus done is giving cerium 4+, like all trapping, and cerium 4+ plus electron is giving cerium 3+ excited. It is an electron trapping leading to cerium 3+ in an excited state, and the excited state is giving again cerium 3+ plus radiative de-excitation plus a photon emission. And so this cerium 3+ plus all plus is giving again by all trapping cerium 4+ for another cycle. We try to understand like this the process of scintillation. The confirmation has been given by using XANES measurement, and it is the most original part of our cooperation, of our measurement in France, in Grenoble. We wanted to confirm this cerium 4+ concentration, you see, and to give a ratio between cerium 3+, cerium 4+ in this garnet. And so we compare now by using XANES spectroscopy in this co-doped and only doped cerium 3+ garnet crystals. We compare also with YAGs, you will see why. This is the site where we work at the European Synchrotron Radiation Facility in Grenoble, you see. We have 49 beams lines, and so we were using this line, ID26, to advance X-ray spectroscopy. I don't, you know what is XAF, which is, first of all, XANES here, and also XAF, but we are using X-ray absorption phase structure. This is the modulation of the X-ray absorption coefficient at energy near and above an X-ray absorption edge. And so they contain information about the elements we are analyzing, about coordination and chemical state. This is the XANES spectra of some reference. You see, we use cerium oxide, cerium O2. You see the first spectra. We use also cerium acetate and YAG cerium single crystal, where in this crystal we have only cerium 3+. And you can see that in the first one, the absorption is completely different from cerium acetate and for YAG cerium single crystal. So we try to use these different shapes of spectra to see if in our garnets we have or not cerium 4+. This is for YAG. You see the spectrum. We did some simulation with cerium 3+. We didn't have any cerium 4+ when we simulate the spectra with 100 cerium 3+ and 0 cerium 4+. And in our crystals, in garnet, first of all, in cerium doped garnet, you see, we don't have any evidence on cerium 4+. We did some simulation with different concentration of cerium 4+, and you see the signal is in black. The signal is there, in black, is there. You see, this is one. The other one are simulation. So we didn't get any presence of cerium 4+. But here, in the co-doped sample with magnesium 2+ and cerium 3+, you see the signal is there. here. And obviously, we see some evidence of presence of cerium 4+ by comparing with cerium oxide reference. You see, and we were able to measure the ratio in this garnet. We got, you see, 0.175 cerium 4+ in this single crystals. So we really detected cerium 4+ in CODUP, and it was the probe that really it is occurring in these materials. So I said that for this material, that the assignment of scintillation mechanism under ionic radiation is not so simple. XANES spectroscopy show the presence of this quantity of cerium 4+, 17.5%, created by charge compensation of magnesium 2+. The UV charge transfer absorption band is really assigned to cerium 4+, like for cerium magnesium CODUP LISO. It is the evidence that the absorption is due to charge transfer band. And I add what cerium 4+ is undesired for photoluminescence application. It is a killer. We say a killer cerium 4+. It really undesired. And it becomes a good activator for scintillating application. It does not give any emission. It absorbs, but does not give any emission. But you saw how it was able to occur. And so it's really very promising for PET medical imaging and fast application due to its high timing performance. What happened now? We want to compare with cerium doped glasses, because we were working also in cooperation with the University of Osaka Engineering Laser ILE Institute, where they are trying to do some experiment. You see the address of the laser Institute of Laser Engineering with Professor Sarukura at Osaka, and also again with Professor Yoshikawa at Sendai. And so there are some specimens of glasses. They are doped with praseodymium, cerium, neodymium, erbium. And for each of them, we were doing a characterization of 5D 4F emission, allow the transition. And we get such spectra, for example, for cerium, doped this glass. This glass has this formula. This is aluminum phosphate and added with lithium fluoride. We need lithium for detect neutron in fusion experiments of so-called GCO12 facility, similar, not at the same energy, but similar to NIF at Livermore and laser megajoule in France. And in this glass, cerium doped this glass, we have detected also the presence by XANES, you see, of this quantity of cerium 4+, you see, 0.25 cerium 4+, the signal, experimental signal is there, you see, and you see there is really the presence of cerium 4+ in this glass due to, is different due to oxidation process during the fabrication of the glass. We didn't add any magnesium 2+, any calcium 2+, but during the preparation of the glass, they pre-exist, and so it's very convenient. And we think that there is an influence on the photoluminescence behavior and probably help to decrease this decay. And so before thanking you for your attention, I would like to give general conclusions with this cerium 4+. We was during a long year, since a long time, some question about the real presence or not of cerium 4+. So here I give you the probe with cerium magnesium co-doped GHGG crystals, garnet, and also cerium doped APLF glass, you see. And it means that cerium 4+ is really essential for fast scintillator. Thank you for your attention.
Thank you very much, Professor Boulon. Are there some questions from the audience before we go for coffee? No. Oh, Professor Suchotsky? Does somebody have a microphone for Professor Suchotsky? All right.
Is it possible to, if you have cerium 3+ and cerium 4+ in certain materials, thank you. If you have cerium 3+ and cerium 4+ expected in certain materials, is it possible to, by some kind of techniques, I mean, process of preparation, like to obtain reduction of cerium 4+?
Only with glasses we got both 3+ and 4+ due to the fabrication of glasses. In single crystals, we have to add some 2+ ions, like calcium 2+ or magnesium 2+. This is our conclusion, you see. It is not obvious.
Thank you.
Okay, thank you very much. I think we should move to the coffee. So let us thank Professor Boulon again.
Thank you. Thank you.
And do you want to say something? Oh,
Thank you.
Yes, and I think, so the coffee, we'll move the end of the coffee break forward about 10 minutes till 4:10. So we'll meet back here at 4:10 for those who are coming back. Sorry, yes. 4:40. It's the dreaded case of the lost chairman. Let's just wait about 2 minutes until people come from the gallery.
Nobody is going to come. So.
Well, the director's over there trying to get them.
Directors, okay.
All right, good evening, everybody. Thanks for coming for the next session after coffee. We'll have 3 speakers in this last session today. So let me introduce the first speaker, Professor Marek Potemski from the Laboratoire National de Champs Magnétiques Intenses, meaning Strong Magnetic Fields Lab in Grenoble. So Professor Potemski has had a lot of collaboration with IFPAN, I think.
Yes.
And one of the sort of main fields of study of Professor Potemski is, I think, electronic properties of 2D systems.
Maybe. Yeah.
Maybe, okay. And, well, the other thing I can say is that since the last couple of years, Professor Potemski has been a member of this Centera project at the Institute of High Pressure Physics, is that right?
You know everything about
I know
me,
everything.
so
No,
it's
no.
fine. Okay.
That's all I know.
Okay, very good.
So
okay.
the floor is yours.
Yeah.
Thank you very much.
Okay. Yes, so thank you very much for inviting me here. And then when I got this invitation, I said yes. But then I started to think, what sort of the talk should I give? And then I asked, and then I thought maybe about something history or something like this. But then Roman Późniak called me and said, no, say something about new, do not be boring, or something like this. So I get trapped, and I'm going to talk about things that I started to do only 2 years ago that I do not understand so very much, but okay, let's share this knowledge. Okay, so I am indeed from the French National High Magnetic Field Laboratory in Grenoble, but for the last 8 years maybe, I was also associated with the Faculty of Physics of University of Warsaw, and for the last year also at the Institute of High Pressure Physics. Okay, so in spite of all of these advices of Roman, I allowed myself to extend a little bit the title of my talk and adding my journey towards magnetism, assisted by Institute of Physics of Polish Academy of Science. So let me start with this subtitle. This has not been said by the chairman, but my PhD was here, somewhere in the department ON4, and my thesis were supervised by Jurek Langer, and this was the years 1980-1986, and at this time, a group of Jurek Langer have been doing much of optics. My thesis subject was a little bit aside, was on electronic transport. And I sort of get in touch with Zbyszek Wilamowski, and this was my first little touch to magnetism, because what we've been doing together was ESR of mobile electrons in semiconducting cadmium fluoride doped with indium. And and this was interesting because what we have been observing is that when you rise temperature, then the line becomes narrow. So this was sort of the motional narrowing effect, while we were thinking that this was the first time that it was observed in EPR spectroscopy in similarity to current actually observations in NMR spectra. And I adore working with Zbyszek Wilamowski, and this has been also many years of friendship and collaboration. Okay, let me go next. So then I've been jealous that my colleagues doing PhD close to me are doing optics. Paweł Ciepielewski, Andrzej Stompor, Andrzej Suchocki, also Detlef Hemmel, and I was doing this, transport. And so then I moved to Grenoble to have a possibility to do optics also, but also changed the subject to gallium arsenide, quantum-less, two-dimensional electron gas, and high magnetic fields. Okay, and then there was sort of the comeback to magnetism. In my career, I was a semi-back to semi-magnetism. What we have been doing in many years of collaboration with, again, Zbyszek Wilamowski, with Grzegorz Karczewski, Tomasz Wojtowicz, Piotr Wojnar, and many others, we have been working on diluted magnetic semiconductors, two-dimensional system made of them, studying electrons and excitons in the systems. And this was also in the form of several former bilateral projects and and others. Okay, so this magnetism is a sort of semi-comeback to semi-magnetism, because what essentially we have been profiting of in the study was this giant Zeeman splitting. That means that there is this famous S or P-SD interaction with manganese ions, which when gets polarized, then they influence the Zeeman splitting of, for example, electrons. And what is interesting is that if you look how the Zeeman splitting changes at low temperature as a function of applied magnetic field. So you polarize manganese. This is a mean field of sort of mean magnetic field created by the polarization of manganese spins that acts first and then increases the enormous giant Zeeman splitting is giant Zeeman, I don't know, giant Zeeman splitting. And what is interesting, and what was interesting for us, is that this Zeeman splitting can exceed cyclotron splitting, which is not the case for normal gallium arsenide systems that we have been studying before. So for example, if you look how H bar omega, so this is cyclotron splitting, and this cyclotron splitting here is much smaller, and then becomes somehow equal. There are intersections of these two characteristic energies. And of course, there are also the same effects in the valence band, and then you can study also exciton with this. Okay, so one of the very first work was on cadmium manganese, on 2D electron gas in cadmium manganese telluride and quantum wells, and then that's obvious. You could observe a nice quantum Hall effect, but this quantum Hall effect was nothing very special. On the other hand, what we have been looking at, we observed that there is some strange behaviors at low magnetic fields in the limit of low magnetic fields. And what happened is, okay, so maybe that is another example of this, and comparison. This is a normal cadmium telluride two-dimensional electron gas in cadmium telluride. So you have in a sense similar behavior as in gallium arsenide. You have oscillations, and then once the magnetic field gets higher, you get a spin splitting, and then the oscillations doubles. Now if you look at cadmium manganese telluride, you have these beatings, and this was of our sort of primary interest. And then this beating you can understand very easily, in fact, because what you what you have is that you have this crossing between multiples of cyclotron energy and the Zeeman splitting. And for example, if you are in a situation that close to the case when Zeeman splitting is equal to h bar omega c, you have the pronounced minima in the oscillations at the Fermi energy, because you are adding this. If you are at, I don't know, 2 times, then you have also. But if you are in a situation that Zeeman splitting is 5/2 h bar omega c, then your gap at the Fermi energy closes and your oscillations vanish. Okay, nothing extremely, so then we could understand this sort of the observations. So what also was of interest was using this cadmium manganese telluride quantum well to go to the situation when your Zeeman splitting goes 0. So the intrinsic G factor of cadmium telluride is such that if you apply magnetic field, then you have this big exchange coupling, but then your Zeeman energy goes to 0. And then if it goes to 0, then one could actually do the experiments in so-called tilted magnetic field. For example, looking at the quantum Hall states at the minimum of quantum states in equal free, changing the Zeeman energy and in principle going through 0. So then this is the result. You observe then this energy splitting between the gap of the fractional of the quantum Hall effect at equal free as a function of the Zeeman energy. And you see that even if you close Zeeman energy, then there is a gap. And this was sort of also of interest in physics, in many body physics of electrons in gallium arsenide. Okay, so we could do this quantum Hall effect, and the question was, what about fractional quantum Hall effect? So first, what we went to non-magnetic cadmium telluride quantum wells, and we could nicely see the fractional quantum Hall effect 5/3 and 4/3, and there was in principle nothing exceptional, apart of the fact that this was the first observation of the fractional quantum Hall effect into 6 semiconductors. Zeeman energy is a G factor in cadmium telluride is bigger than in gallium arsenide, so the observation here was that both 5/3 and 4/3 fractions are spin polarized, in contrast to this what is in gallium arsenide. And then we went also to, in collaboration with the Dieter Weiss group at Regensburg, and obviously all our Polish collaborators, we could do also fractional quantum Hall effect in cadmium manganese telluride, and then there was a competition again between this Zeeman splitting, which we could tune with respect now to composite fermion structure. Okay, so maybe now. Okay, now optics has been also done, and this is a little bit more than a single particle or simple, well understood, let's say, or roughly well understood effects of quantum Hall effect and fractional quantum Hall effect. We could do also optics, and this is one of the example in which we could look at the with Raman scattering, with magneto-Raman scattering. We've been looking at manganese spin flip transitions and at the electronic transitions. Again, this is this characteristic Zeeman splitting, and the observation here, what was sort of most important for this paper, is that there is anti-crossing between them, and then there have been papers saying that this is the manifestation of collective character of these two excitations, and speculations about that ferromagnetism also appears in N-type cadmium manganese telluride, but at temperatures which are of about 5 millikelvin. Okay. We work also on quantum dots, showing that actually if you have a single quantum manganese dot, you have in the system so-called bright excitons, which follows the selections rule delta S equal ±1, and then you have those which follow ±2. Those ±2 are not active, but they become active in single quantum dots of cadmium telluride with manganese by simultaneous inversion of the manganese spin. Okay, I don't know whether Grzegorz Karczewski is here, but I think that I had the privilege once to be with him within an MB system here, and I think we both grew the first single dot cadmium telluride dot with a single manganese ion. Okay. So let me go now to the bulk of my talk. So then, after this excursion to magnetic systems, we get interested in graphene, and then afterwards there have been a lot of work on monolayers, bilayers, and thin layers of transition metal-optical coordinates. But then the latest interest was in this in antiferromagnetic semiconductors. So those are also layered materials. You can exfoliate them, and to say the truth, those systems have been studied a lot already years ago. And but the conclusions of this review paper about the system. That due to the complexity of the unique cell, there is no detailed calculations on their electronic structure which can explain in a satisfactory way the observed experimental evidences. Therefore, it's necessary to deduce more information experimentally, and so on and so on. And all this is still true. We still do not understand, although we are speculating about application of this system in nanospintronics. I don't know what does it mean. Magnon spintronics, terahertz technology. And of course, when talking about monolayers, sometimes we are referring to sort of the statements that there are no magnetic order in strictly 2D system, but that's only in a very strict case of Heisenberg antiferromagnets. But those probably do not exist. Okay, so the work has been done by my young collaborators, Dipan Karjana, especially I adore to work with him, and also others, Diana Wacławkowa, Piotr Kapuszczyński, Amit Pawbaker, Jan Wyzula, Iwan Mochelski, and also my more senior collaborators, Clement Faugeras, Milan Orlita, and also our collaborators from abroad and from the laboratories close by in Grenoble. So our main focus is going on ion phosphorus sulfur and on NEPS3, and those two are at the same time similar because they are so-called zigzag antiferromagnets. So in a hexagonal cell of this, you have free spins which are up and free spins which are down. So still antiferromagnetic, but the spins in FEPS3 are aligned perpendicularly to the layer, whereas in NEPS3 they are aligned in the layer plane. Both are semiconductors with gaps, which are still a question of sort of uncertainty, but about 1.5 electron volts. Okay. Okay, so if we talk about antiferromagnetic order and characterization of this order, then we are talking about Hamiltonians, about all of the terms in the Hamiltonians, so exchange coupling, single ion anisotropy, dipole-dipole interaction, and then we would like to extract these terms to describe the antiferromagnetic order. And of course, I am from the Heimlich lab, so we applied also magnetic field. So another characterization is also G factor, but it's also that magnetic field changes the phase of this antiferromagnets, as I will talk a little bit later. Okay, so how do we do it? And the most powerful method, at least as I see it, a beginner in the field, is inelastic neutron scattering. And then you measure with these methods as our collaborator Andrew Valdez is showing us and teaching us. You can measure the dispersion relation of the spin wave excitation of magnons. And then once you know this, then you can find all of this. You can model it. You can find this exchange constants and so on and so on. But it's not that easy, because if you have this dispersion still that is not fully clear what sort of set parameters. You can model it with a different set of parameters or different form of Hamiltonians. And also neutron scattering also are suffering from the limited, let's say, resolution. So optional methods so for example, in case of this, I would say most probably simple antiferromagnet, but still not really understood. The neutron scattering is saying that there is a magnon gap at a fixed and non-zero. Actually, still under discussion what is the reason for this non-zero gap. And is double degenerated. And then the optional method is to use this, to study it, is optics. But with optics, again, we do not have access to all the dispersion. We look at the k equals 0 excitation, because photons do not have any photons, they do not have momentum. So, but what we can do is that we can do it as a function of magnetic field, and that is sometimes called antiferromagnetic resonance. And for example, this is what you get when you do this in manganese PS3. So you get this characteristic antiferromagnetic resonance with two branches, but at the same time, because your resolution is better, you see that this gap is in fact not double degenerated, but there is a small splitting. So in fact, this conclusion here is that the manganese PS3 is not is a biaxial and not uniaxial antiferromagnet. Let me go to next. So FePS3. FePS3 is a little bit more complex. As I said, has the zigzag structure. And then the dispersions of in FePS3 are a little bit more complex. There are two branches because the cell is doubled. And again, they have been studied, and then Hamiltonians were simple, but then also the parameters used to describe this results have been changing, and then we also tried to apply our optical methods to this. So again, first we focus on this lower energy gap, and as a matter of fact, optics have already been applied to FePS3 for a long time. And many papers have been, and the results are more or less like those which I'm showing here. So there have been not initially the experiments as a function of magnetic field, but there were experiments as a function of temperature. And what you can see is one particular mode here which shows a strong temperature dependence. It sort of softens with temperature and then somehow merges. And then the question is, what is this mode? There have been many papers and many history of this small peak. Is amazing because first was attributed that this is a phonon mode, and then at a certain moment those people working in Paris, they figured out that this is a magnon excitation. but then it has been forgotten. And then a Korean group published nanoletters that again interpreting it as a phonon, and then the American group finally has shown that this mode does splits into two components, which clearly shows again that this is a Magnon excitation. So Diana did a little bit more, extended it to higher magnetic fields, and what you can see here is that now you have these branches which go, but then there is a phonon, and then these Magnon branches do interact with phonons. So as a matter of fact, you have sort of the Magnon polarons. This can be understood. There are conclusions that you can see the strength, so those magnons are coupled even at zero magnetic field with phonons. There is a zero field splitting again of this Magnon branch because of this coupling to phonons. And we also think that because these are coupled Magnon-phonon modes, they are electric dipole active. Because you can see them clearly even if you do a normal Fourier transform transmission experiments. This by Amit Pavbake and Clément Faugeras, we also applied hydrostatic pressure and then repeated the magnetic field evolution of this Magnon polarons at different pressures. What you see here is again that one confirmed the splitting of the Magnon due to interaction with phonons, but also one confirms the following thing. What you can see here is that Magnon as a function of pressure in fact does not change the position, whereas phonons do. So essentially this means that FEPS3, even in a three-dimensional form, in a multi-layer form, is a two-dimensional magnet. Okay, and then come a little bit more complex things, because this antiferromagnetic resonance, it's a simple image of, so if you forget about all of the spin waves and you think only about ion 2 plus with a spin 2, and you think about the spin resonance of this, so the transitions which are possible are plus minus 1, so between the adjustment levels, but you could also imagine that you have other transitions. So for example, the transitions from -2 to 2 state. Of course, that's forbidden. It can be allowed under some conditions. Of course, spin-orbit interaction is a messy interaction, and it can be made more. This type of the different possible transitions for a single ion transforms also in a zoo of different antiferromagnetic resonances, and in particular, this which is called single ion 4 Magnon bound state, which somehow resembles this inversion of spins by a factor of 4, and this has been seen. This has been seen by infrared spectroscopy. So again, this one Magnon, or the one Magnon and one Magnon, this upper branch, you can see a typical antiferromagnetic resonances, but then you can see also another antiferromagnetic resonance, which is due to this 4 Magnon stand, which shows the G factor, which is 4 times bigger than that for the normal resonances. And then these Magnon polarons have been also found in other antiferromagnet, pretty similar to FEPS3, but now as sulfur is replaced by selenium, and that changes quite a lot apparently, because now this coupling between phonons is sort of selective. So you have two phonons which are almost degenerate, and you have two Magnons which are almost degenerate, and now this is this phonon which interacts with this Magnon, and this phonon which interacts with this Magnon. So there is a selective coupling. Selective coupling, and besides this, the Magnon is already splitted even without coupling, so it's a biaxial also antiferromagnet. Okay, so let me go. How much time do I still have? Oh, no. Okay, so let me go to neutron scattering of nickel phosphorus sulfide. Again, this was measured by neutron scattering, and the things were, again, evolution of parameters and Hamiltonians to apply it. And one of the issue was all the time whether this lower branch in NEPS3 is a branch that is gapless, so these low energy magnons are so-called acoustic magnons, or there is a gap in the spectrum. And this is what we have been trying to do. Again, there is a history of this. People have been looking at phonons, no problem with this. But then Dipankar managed to measure it also excitations very close to the laser line, and these excitations have the function of, they are showing a typical softening with temperature as a function of temperature. So there have been magnons, and then this has been confirmed with magnetic field experiments. Extremely tricky because your spins are in plane and flakes are small, and one has to manage to align actually magnetic field with respect to spin orientation. And that was a big experimental challenge, but somehow done. And the result was that actually again NEPS3 is biaxial antiferromagnet, and this lower so-called acoustic branch in fact is also gapped. Now I'm going to the last part of my talk about things that I must honestly say I do not understand, but which are sort of very much appealing for me, is that, for example, if I take this NEPS3, there's also an optical transition, apparently now around 1.5 electronvolts, and this optical transition is extremely sharp, 300 millielectronvolts. Whatever it means, and it exists only in the antiferromagnetic phase. So when you do it as a function of temperature, then it exists. You can see it in reflectance or absorption. You can see it in emission. And there have been a number of papers which have been reporting this, and one of them have proposed extremely challenging or a challenging interpretation for me as a coherent many-body Zankreis exciton. And in agreement with this interpretation and challenging interpretation, it has been shown that actually there is no magnetic field effect of this, and this transition is not sensitive to the application of magnetic field, which appeared not to be true. And again, this is due to Dipankar, who made a really challenging experiments. If you apply again magnetic field in a direction which is very much along the spins, then you see a splitting of this line, and it is very much sensitive to magnetic order. So the issue is now what is origin of this transition, and okay, so this challenging interpretation of many-body coherent exciton, but apparently it is sensitive to magnetic field. So we sort of invoked a little bit more trivial speculations that this is the internal transitions within the DD states, D states of manganese ions, of nickel in this case, 2+ ions. But then the question is, why so sharp? What it is only active in the antiferromagnetic phase? But what I would like also to say is that it is nickel PS3, and this transition is not the unique thing. Also, you have this transition also in other in other layered materials. So this is manganese PS3, and again there is a transitions relatively weak, and then the Pankar is now showing me samples of better quality, which shows that again this is extremely strong, extremely sharp transitions, which again shows correlations with magnons, and then also in other like chromium PS4, which is not the let's say antiferrous, which is a little bit different system. I don't want to go to details because I would like to finish at this moment. But again, there is a transition, again pretty sharp, which only exists in the antiferromagnetic phase, which is sensitive to spin ordering, which collapses, splitting collapses at the spin flop transitions, and so on and so on. Okay, so let me then finish and with the conclusions that I hope I convinced you that magneto-optics is a relevant tool to study the layered semiconducting antiferromagnets. And then this, at least this is my sort of point of view, personal, that physics of the spin entangles or sensitive to magnetic order optical transitions in this antiferromagnets needs to be understood. And okay. But at the end, I somehow have in mind this cadmium manganese telluride, where you also have optical transitions which are sensitive to actually by simple spin polarization. So what is the relation between this and this needs to be clarified. Okay, thank you very much.
Okay, thank you very much, Professor Potemski. Are there some quick questions that the audience would like to ask?
But only simple, please.
So I was going to ask a quick question about the outlook, but I guess you sort of showed that with the manganese in some sense. Is that sort of the next direction?
I don't know. Coming back to Institute of Physics, asking help Jacek Kossuth.
Okay. Thank you very much. Let's thank Professor Potemski again.
Thank you.
Let me introduce our next speaker, Professor Antonio Bianconi. Do we see Professor Bianconi? He's coming. Okay. So Professor Bianconi is the director of RICMASS, the Rome International Center for Materials Science of Superstripes. He got his PhD in 1969 from the University of Rome. And he's the leader of many research programs. From his CV on the internet, he was the author of 7 books. It could be more now, I think, if that's true. And as far as I know, he's, for example, very well known as the organizer of these Superstripes conferences that have been going for several decades, I think, now. So thank you very much for coming to our celebration, and the floor is yours.
Okay. Okay, I'm very happy to be here. I will speak a little bit about the history of science and the last results we got a few months ago. So the topic is superconductivity, so 1911, and quantum mechanics 1925, and room temperature superconductivity very close a few years ago. So superconductivity remains a little bit a mystery. So there is no theory predicting superconductors. So all the discovery of superconductor has been done by trials and errors. And perhaps we are at a point where we can design superconductivity and ITC superconductivity by quantum design, and to predict exactly the seed of material. That is a very big steps in history of science. I started my career in '69 in liquid helium, but my first conference was in semiconductor conference in Warsaw in 1972. And then we met, we made very good friends in Poland. And in 77, I was building the first beam line in the synchrotron Frascati. That was the only synchrotron in Europe at that time. And Kiesel from Kharkov came to Italy, and we started to do palladium hydrogenation, palladium hydride superconductors. Then the synchrotron this was down, shut down. And then we started a new project with the Gdansk group of Zosky and Kalinowski on organic semiconductors. So we already the idea of, and then in the 90s with ITC superconductivity, we had a very, very good collaboration for many years with Roman Miknas of Poznan and Andres Olesh of Kharkov. And in these last 20, 30 years, we have a good collaboration with Roman Pusniak in different topics of ITC superconductors. So I thank again Roman Pusniak for inviting me to come here. But it's a very nice opportunity to develop more collaboration between Italy and Poland on these topics that I will speak in this talk. The topic is essentially a new results that we got recently published in the Journal of Applied Physics, where we did experimental mathematics. So it's a theory that completely mathematical with no approximation, just basic quantum mechanics, with no standard solid-state approximation, BCS approximation, just to do everything by first principle, and to have in the same time a material grow that we can interact independently between the theory and experiments. So all the theory is very well explained in this paper. And the story is that we focused on the superconducting dome of cuprate superconductors. So Alex Mueller discovered this in '86. And there was very early results that you have a dome where your superconductivity appear only with antiferromagnetic Mott insulator with 0.5 doping and end at about 0.25. So these are the experiments repeated many, many times, but nobody really made a prediction. So create a material that has this kind of dome. Okay, so the time go fast. So this is more than 35 years. But some groups started to think that our approximations that have you seen in this meeting all the day, we have seen how now the physics is looking to complex materials. So physics always was looking for approximations. So on the contrary, it's possible today to go to this complex material that this morning was discussed many, and also there is the previous talk. So the system is much more complex than we can simplify by the physics. So sometimes theoretical physics become an approximation physics. On the contrary, we need experimental mathematics. So in mathematics, pure mathematics, that is predict an experimental fact, and experiments do in this way. And if you are really knowing these days how it is important, you have seen also in the previous talk that you have not a spin glass, you have not a spin program, but you have many, many different quantum configuration. And then you have to go back to the initial time of quantum mechanics. And in 1996, we made, with synchrotron radiation, we just measured without any bias, without any prejudice, just experiment with X-ray spectroscopy with synchrotron radiation. And we came out with some numbers that there are stripes of the order of 8 angstrom that are doped by strontium. And then there are stripes, there is no doping at all. And the size of this undoped stripe is 16 angstrom, so 1.6 nanometer, 96. So in 96, this number was impossible to do a superlattice of this way, because superlattice in this way of quantum wires was 200 angstrom. So we had a guess in this time But at the same time, we started to do, so we made a patent, but it was impossible to create materials like that. So the people that was believing to nanoscale phase separation were very few people. And you will see that also in Poland, they started with Późniak also demonstrated the presence of nanoscale chemical phase separation. And we started to do mathematics. We are small groups of 3 people in 3 independent groups working for 30 years to improve mathematics with the theory and experiments. And okay. So we made the patent that you can do quantum superconductivity with quantum wells, quantum dots, quantum wires. But they took now other 30 years to demonstrate that actually it's possible to do and to calculate and to do. Let me go fast because so the idea is that you can create a NATO structure of a superconductor like chocolate and almond white. It is like a cremino cookie. Alex Müller liked very much this idea because his grandfather was the discoverer of cremino cookies with chocolate in Switzerland. He made a lot of dollars. So the basic idea is very simple in this community because we have a quantum size effect. And in quantum size effect, you have 2 different bands due to S and P waves. And then you can have superconductivity between the two. You have a pairs in one band and pairs in the other band. So this is completely beyond any BCS approximation. You have to use Bogoliubov theory. And if you take it to interpret this story, the story go back from Majorana. It's called the effect is called the configuration interaction between open and closed scattering channels. Majorana called it the quasi-stationary and quasi. So it's a very long story. So 35 Ugo Fano, 37 Tomonaga, 58 this is time where the physics Institute of Warsaw was founded, 53. And Weishaupt had this idea of developing Bogoliubov. I don't put here BCS because BCS is a very quasi-classical theory. And then Fano-Feshbach, Blatt, Kondo, Leggett, Volovic. So this is our fathers. And we just developed this kind of idea. So we have to deal with a condensate with one many-body wave function and another condensate. We have 2 condensate. And the gap, you can have many gaps. So gaps, one gap depends on the other gaps. This is a standard Bogoliubov theory, and this is what we followed, improving the computer code for many years. Okay, I don't go in the details, but in the details, the Fano-Feshbach interaction between a local pair and a delocalized, completely delocalized band, you can have a real resonance, not only a mixing, but really a resonance between the two. And in the resonance, you have that when you have a boson Fermi model, you have a back BCS crossover, back BCS, you have TC go down. Then you have an intermediate, very high peak when you have a intermediate decays, and then you go down to the BCS limit. So what we claim is that this was a Fano-Feshbach resonance between a BCS condensate and a BCS back BCS crossover. So that is between these 2 limits. So the advance we did now in 2021 with Raimondi and Mazzotti and a group of mathematicians, essentially, we make the simple case where you have a superconductor and you have a potential barrier, and at interface, like you have a PN junction, you have an electric field. The electric field is at the interface, and the electric field creates a Rasbach spin-orbit coupling. And then you treat everything without, not with Gorkov Rasbach approximation, but everything from first principle So the computer code is very big. And what is more important is to solve the not the Schrödinger equation that has no spin, but to introduce the Dirac equation. This was the biggest effort we did. And we calculated the Dirac wave function without any approximation. And then we came up with very simple predictions. So you have the quantum wells, the states in the quantum bell become have a different helicity, and then you can put the number. You can put the number of 2.5 nanometer. So it's the same number we had already by X-ray absorption. And then you calculate by first principle the electronic topological transition between the first and the second subband. The Fermi surface becomes sophisticated. So you have a very complex scenario. So you have here the first band remain always a two-dimensional cylindrical. On the contrary, the new band appear. You have a band with two torus, and then become a very strange. And then the quantum critical point become a line, and this strange topology give you the resonance. The resonance was calculated by Maciej, published 1 year ago, exactly, November 22. And you get the maximum TC that you can get 140 Kelvin. You can reach a quasi maximum TC, but then you can have everything up to 40 Kelvin. So you can adjust the electron phonon. You have two parameters, the electron phonon interaction and the Lipschitz parameter, so the distance from the appearing of the new Fermi surface. So it looks like a mathematical game, but it's all mathematics founded with no approximations. And then with Logvenov, we met 1 year ago in a Stripes conference in 2022, and he said, but we can create your superlattice in Stuttgart. We can make exactly with a very sharp. We can make layers of 2 nanometer and 1 nanometer of superconducting and insulator, pure lanthanum 2 copper 4, and this is lanthanum 2 copper 4 doped by 0.5, so metal with no Mott. It's a simple metal. It's not a Mott insulator. It's not a charge transfer insulator, and we can create this by a repeat of 10 times. If we 10 times we calculated the repeat of 10 times was nearly infinity, so it was very good. And then we started to grow different superlattice. With a period about 4 nanometer and 3 nanometer. So everything appeared between 2 and 4 nanometer. So in this superlattice, you have a lanthanum 2 copper 4 that is 2 nanometer large, so completely antiferromagnetic. And this one is completely overdoped, 1.5 nanometer. So you have something that is, Logvenov was working on these materials for 15 years with Bosovich. But he never was able to predict. There was no guess what will do the TC. And they had hundreds of trials and errors. So we say to him, you need to make the metallic 1.23 nanometer. And you have to do the antiferromagnetic 2.5 nanometer. And you will get TC 40 Kelvin, he got. So we worked for 1 year, we produced 55 samples. We gave the number, he made the samples independently, and they correspond always. So the idea is the following. If you take, is what we worked for 30 years. So if you take the superlattice, and then you have the metal and the insulator, you have a PN junction, and then you have the space charge that fill the antiferromagnetic lattice. So the antiferromagnetic lattice is not doped by chemistry, but is doped by space charge like in semiconductor. And then you change, you have the quantum size effect, predict two subbands, but then changing the strip, the thickness of the lanthanum 2 copper 4, you create two sub-bands, but you can, if you make it too short, too small, it will go up. If you make it too narrow, it will be mixing. And so you have changing the ratio between the metallic and the insulating part, you can predict exactly. So you have now but what is important is that what is important is that now we can produce energy, we can tune exactly, we can create a material where we know where is the topological Fermi surface, we know everything, we can calculate everything, and then you can grow and you get what you have calculated. So the important point is that it's not a BCS because you have the matrix elements are very important, and then you can produce this is essential picture because you can have a geometry factor that is the ratio between insulator and superconductor, and here you have the distance from the electronic topological transition, from the Lipschitz transition, and you have this strange two-dimensional plot. But then you can see the experiments you can make as function of the geometry factor L divided by D, or as function of the Lipschitz transition density, and you have a different domes. This is a geometrical factor, and this is you see that we predict exactly the onset and the drop. And here you have a function of doping. The onset is at 0.05 and the drop is at 0.25. There is no any trick. So the samples are very stable. We can send to everyone the samples. We measure it after 1 year, and they have the same TC, and you can make all kinds of experiments. We can send you the samples, and you can do. They are 10 by 10 millimeter, 10 by 10 millimeter, or 5 by 5 millimeter, and you can have contacts, and you can make all the pattern and mesa you want. They are very, very stable. This is TC as function of temperature. This is a two-dimensional resistivity, and you see you have they look like cuprates. It's artificial cuprates. So now for 35 years, people were studying cuprates without knowing where strontium was. Now you know. The strontium is made where it is. So there is no more this mystery. Where is doping? Doping now is very well controlled by 0.1 nanometer, a few angstrom precision. And then you can see you have everything is fantastic. They're very reproducible. And this is a geometrical factor that can change TC, go up and down and come back. And if you take the average doping, if I give you the sample that you don't know, you say this is like average doping, and you measure TC, you see you have the dome. But you can have also a function of the geometrical factor, and you have the onset and the drop. So the thing is very promising to change the field in such a way that now the system becomes a quantum system like ultra-cold gases, where you do first quantum mechanics calculation and then you make the experiments to verify if it's correct. Like the Feynman sentence that von Klitzig was citing, the quantum physics, the physical law should predict exactly the experimental results. And there are some so I think we come back to the first time that perhaps we have solved the problem of the dome, and I don't know how much time. I went very fast, and okay. So this is the results. We have this. You can change the period, so the period can be 2.97, and 528 nanometer. What is important for the maximum TC is when you have this 2/3 ratio between superconducting and you have in this is quite universal, is 2/3 between the thickness of the superconducting layer and the thickness of the barrier. And the variation of this variation, we have many samples with 1.98 period or 528. So the material is not when you have 10 repeats is 52 nanometer. So it's 52 nanometer, so it's microscopic stuff. So, but you can have all the quantum mechanics. I think I would like to say that we would like to develop. We are making high magnetic field magnetoresistance. We are doing terahertz experiments, but we are very happy to exchange and collaborate with all groups that want to study these materials, because and you can also grow and we can also interact with help the system. So we have been very excited. It was one more exciting time in my life. And Logvenov made a fantastic work. It was an example of Galileo experimental method. So the theory should be only the theory, and the experiment should be only the experiment, with no bias between the other. And in the end, you compare. This was the big lesson that we did. With Logvenov was fantastic experimentally. I am experimentalist, so we were doing experimental theory, experimental mathematics. And but it's possible today. So with a big computer, you can do that. So is now also what Dieter is doing in his talk. You have this nano cluster in the system, but you didn't know. Then with nano X-ray diffraction, we arrived to this point with nano doing very fun update nano X-ray diffraction in materials. If you take a lanthanum 2 copper 4 doped with the nanoscale material, you see with the solution of nanometers, you see that there are quite a different place in the inhomogeneous materials, where perhaps the nanoscale grain are the origin of the macroscopic report. And so this is what we learned, and I would like to share with you these results. Thank you for your attention.
Thank you very much. So from my end, coming from this ultra-cold atoms, which you mentioned, it seems impressive to me.
Excuse me?
So I'm actually from this ultra-cold atoms that you mentioned. And it seems pretty impressive to me, because, I mean, I've always been told that these things are difficult to predict.
Yeah,
Do we have some questions from the audience? Yes, over there.
What was the method you used to grow these superlattices out of?
Excuse me?
What was the method of the growth?
Molecular beam epitaxy.
Which?
Molecular beam epitaxy.
MB.
Yeah,
Okay,
MB. With it's important that you have a several year. You can the theory. This is what I didn't say. The theory don't make assumption that is a strongly correlated material. So we think that you can realize the same predictions also for lead bismuth materials for many different kinds, because this is an amplification is an amplification and is an interference effect. The dome is an interference effect. You have a positive interference, you have the maximum. And at the two border where you go to zero, it is a negative interference effect. So the dome, everyone was, you can calculate the dome in superconductivity. You can calculate the superconductivity of 40 Kelvin. You adjust the parameter, you get. But you don't get the dome. Because what we get is not on the coupling, but is in the matrix element of the pairing. The matrix element is determined by exchange interaction between pairs. And this is what I show. The negative, the drop that is fantastic predicted is a negative Fano interference effect. It's not coupling. Coupling is always the same. So you have a negative, and then when you are at the top of the dome, you have an amplification. So the pairing term, you can go to 200 Kelvin, 250 Kelvin. We calculate up to 250 Kelvin. And you have the dome at 250 Kelvin. But then what is important is that you get the limit of the dome that is the negative anti-resonance. And the Fano that was my supervisor told me always that in the Fano resonance, it's not important at the dome, but at the negative effect. Because when you have a negative interference effect, it's really quantum mechanics. So there is we expect that to collaborate also for choosing different materials, but you have to know already the chemistry of the material in order to have very sharp one angstrom precision with 1 lattice units. So if the lattice units, for example, in this case is 13 angstrom, but you need the precision of 2 angstrom for the interface. Also, if you have a little bit of indetermination because of diffusion of atoms, but you have to be able to keep it below 2 angstrom, 2-3 angstrom. It is a very incredible achievement of the modern technologies, I think. It's not, but what is interesting is that there is a proposal of a shift of interest from the strong coupling or weak coupling to matrix element effect of a pair transfer term. And this can be calculated with the modern computer we have today. So,
okay, thank you. Any more questions from the audience? Professor Story?
What would be your strategy to go to room temperature?
There is not a problem. No, we get up to 250, 260 Kelvin, no problem with coupling at 0.3 and with phonon energy, so standard numbers. It's not a problem. We did 3 papers on high pressurized materials. We get the RMS results. He has not a complete dome, but up to, so from the quantum calculation, we reach a room temperature 280 Kelvin. More is becoming, so you have to find over to change the coupling in some way. So it's
So what actually limits this particular material to about 40 Kelvin?
No, this was only because we had the samples of log Veno was 40 Kelvin. Maximum.
So it's a property just of this material.
We adjusted to get 40 Kelvin and then we calculated the dome. So but there is no adjustment. We put only coupling. Okay, for 40 Kelvin, coupling is at 0.3 and the phonon is 60 millieV. Then if you increase the phonon from 60 millielectron volt to 120, and then, or you increase up to 0.4, you can increase electron phonon coupling, but you can also have a magnetic, only magnetic interaction, because we calculated the matrix element of the pairing, not the coupling, or the coupling is dependent materials. So you have to choose the materials. It's here in the RMS materials are hydrogen that have very high frequency, 100 millielectron volts, and the electron phonon coupling is 0.35. And then you get the 200 Kelvin. But I don't know if we can get 400 Kelvin. I don't know if we will never get. But up to 280 Kelvin is possible. No. And in fact, also improving with RMS the results. And now we have a multi-gap, because you need a multi-gap. With a single gap, you cannot. But with a multi-gap, because you have interference effect with exchange transfer between the pairs, Pogulubov theory. So it's possible. So it's no.
Okay, thank you very much.
You have my email. You can write us if you want to have a collaboration, because I see you have a lot of know-how on this field. So to have maybe taxi materials. Okay.
Let us thank Professor Bianconi again. Thank you very much. And so let us move to our last speaker, Professor Dr. Andrzej Szymko from CERN. And if I can introduce Professor Szymko. So he studied at the Warsaw Polytechnic, did his PhD here at the Institute of Physics in 1992, and I believe moved to CERN soon after. And at CERN, he's a group leader of the Machine Protection and Electrical Integrity Group in the Technology Department. Is that? That was a few years ago. Yeah, this is what I suspected. Sometimes this might not be accurate. In any case, the floor is yours. Thank you very much for coming.
Okay, thank you very much for your introduction, and thank you for inviting me to this event. I'm really honored. And it's also a great pleasure to be here. For me, it's always a pleasure to come back to the origin, to the place where my career started, and I will always remember this period for sure. So, like other speakers, I've got also some indications from Professor Późniak, what should I present. So in my case, it was rather simple. Say what are you doing at CERN and what you plan to do. So what I will present to you today is first I will start with a short introduction just to set the scene, and then I will tell you about the accelerators, what we are using today and what we plan to do in near and a bit more distant future. And then I will present also some experimental results and work that we are doing at CERN. This will concern particle physics, but also nuclear physics and atomic physics. And this will be focused on Poland's contribution to those experiments. This won't be an overview. This will be just selected examples, because the overview would be a bit too long for today. So a few words about CERN. CERN, it's pretty well known. So it's a basic research laboratory, and our main objective, our main mission is to make a basic research, and we are investigating the particle physics and forces between elementary particles, trying to understand how all this is working. But this is not the only mission. We have also other missions. So first of all, we need the technologies to make experiments in high energy physics today. Really high technologies are needed, and we are developing this. We need also scientists doing this, and we are really involved also in education and training. We have a number of schools that we are running every year, dedicated to training of next generation of scientists and also engineers that are needed in our domain. And the last, but very important, it's collaborations, organization of collaborations. I will come back to this a bit later. So a few numbers about CERN. So CERN was created in 1954. So CERN is much younger as compared to Institute of Physics of Polish Academy of Sciences. We will have a 70th anniversary next year. So CERN is formed by member states. Today we have 23 member states. Poland is one of those member states. But also we have other categories like associated member states, observers, and many other countries that are just cooperating with CERN via cooperation agreements. So today, in numbers, what you can see that we have nearly 2,700 staff members, 900 fellows. Fellows are either PhDs or junior fellows are just graduated. And we have so-called users. This is fluctuating, but it's around 12,000 and 1,500 of other categories. So at CERN, we can say that about more than 16,000 people are involved. Of course, not working at CERN, because at CERN we have around 6,000 to 7,000 people working. So this is just a few numbers concerning the CERN. On the top of those numbers, I just prepared some numbers for Poland. So from Poland we have 316 users. Users are just scientists who are normally working at universities or home institutes, and they are just coming for a period of time to make experiments to work at CERN. So from Poland we have 316 users. We have more than 90 staff members and 67 fellows. Those are the numbers from the end of last year. So now I will switch to accelerators. A few words about the accelerator complex. So at CERN we have many accelerators. People are normally familiar that we have a Large Hadron Collider, but this is just one of the accelerators. We have a whole complex, and today we are operating 9 accelerators and 2 decelerators, and Large Hadron Collider is just the last element of the acceleration chain, because they are all linked. They form a chain. And the Large Hadron Collider, it's operated this year at 6.8 TeV energy per beam, and for the collisions we have 13.6 tera-electronvolt at the center of mass. So the accelerator complex serves not only the LHC, but it's used for many other experiments, and this is a bit not so well known. So that's why in the next part I will tell you more about this. So starting from LHC, which is the flagship, this is 27 kilometer in circumference double synchrotron that is colliding basically protons at 13.6 TeV energy, but also is colliding, and this is right now we have an ion run, and we are colliding lead ions. So the main achievement of LHC was pretty well known discovery of Higgs boson in 2012. So this is, as you can see, what was here. We have the main parameters for LHC. This was the design parameters. So here you can see what was achieved. So concerning the energy, we are nearly there, but we didn't reach yet the top energy for which LHC was designed. But if we take another parameter, which is instantaneous luminosity, then this we exceeded significantly by a factor of 2. And this was the design integrated luminosity. Okay, not everybody is probably familiar with what luminosity means, but this is a measure of a number of collisions that accelerator can produce. So this integrated what was designed for the total integrated period of lifetime of accelerator. So we are approaching this slowly. So I had to mention this, but at the very beginning of the R&D for LHC, Institute of Physics of Polish Academy of Sciences contributed contributed into the development of what we call today very classical low temperature niobium titanium superconductors. And what was studied here was the magnetization of those conductors. And this was very important for the LHC, because this was a quite critical parameter impacting on design of a whole accelerator. Whole magnet system was awaiting the conclusion about what can be obtained concerning the magnetization of this type of conductors, because depending on what can be obtained, then the correct correction systems had to be designed and implemented, and so on and so on. So this was very important for LHC, and this was it was done here. So what we are preparing, what we are working on now, I mentioned that we are slowly approaching the luminosity, integrated luminosity for which LHC was designed. And what we are preparing right now, we are preparing an upgrade of LHC to so-called high luminosity version of LHC. This upgrade will basically require replacement of a number of final focusing magnets around two experiments that we call them high luminosity experiments that are producing most of the collisions in the whole accelerator, and unfortunately, due to this high number of collisions, they are also producing a lot of debris and radiation. So that's why the lifetime of those elements is pretty limited. So we have to upgrade this to the new version, and this will be a next generation that will also allow significant increase of number of collisions in future. So justification for this, there is of course a lot of physics cases that are considered by physicists that needs to be addressed, but also and this is very, I would say, prosaic, that the goal is also to exploit the LHC to the maximum, because without replacing those few elements, all the rest we won't be able to use. So that's why we have to replace those small sections of LHC just to profit from the existence of dress. So this will be done in the way that the goal is to increase this integrated luminosity till the next stage, till the next duration of life by a factor of 10. And this is very important also from the precision of the results that are obtained by experiments, because they are proportional to the volume of data. They are proportional to the statistics. So, as stated here, that if you would like to increase the accuracy by a factor of 2, then we need 4 times the data to do it. So this is ongoing. Here you can see few examples of equipment that is being produced. Those are the examples of magnets that are produced either at CERN or in American labs, in Fermilab and in BNL and LBNL. There is a lot of other equipment that is also produced. So this is ongoing, and the timeline for implementation of this is shown on this plot. So we are here. So we have here right now we have a run at 13.6 tera-electronvolt, and we will continue till end of 25, And then we will have so-called long shutdown free. This is the way how accelerators are operated. We are operating this for a couple of years, then we stop to make upgrade, to make improvements, and the long shutdown free will be dedicated to the upgrade of LHC to high luminosity version. This will be a pretty long stop because this will take 3 years for LHC, but not for a whole complex, only for LHC. And then LHC, as a high luminosity LHC, will continue till end of next decade. So this is the plan, and where we are, as I mentioned, and as I demonstrated on those 2 slides, we are in the construction phase of equipment, and we are preparing the installation phase that will start in 26. And physics will continue after the long shutdown free. So this is what's going on at present. So now a couple of slides about the options for a more distant future, because the high luminosity will be operated till 2040, maybe 2042. So we are thinking about the more distant future, and there are several options that are considered for the second half of this century. So we are considering options that are either hadron colliders, like LHC. LHC is a hadron collider, but also we are considering lepton colliders, circular, and also linear colliders. So all this is, we have pros and cons, and this is being evaluated right now. We are doing this evaluation via a certain process which is called European Strategy for Particle Physics, and we are updating this strategy every couple of years, every 5 years, and the process of an update takes roughly 2 years. So the next one will start exactly at the long shutdown free in 26, and in 27 will have to be concluded. So the previous update, the conclusion of a community, but not only of a community, was that the so-called future circular collider, it's the preferred option, and this should be done in 2 stages. First stage, this should be designed as E plus E minus collider, serving also as a so-called Higgs factory. And then in the second phase should be refurbished and form high energy hadron collider. So this was the previous strategy, the conclusion of. So we are doing this. So we are working on feasibility for such colliders, for such versions, and this is just a picture showing how this future circular collider may look like. So you can see that Geneva is somewhere here. This is the airport. This is the present LHC, which is already gigantic. And this is the planned future circular collider at CERN. So as I mentioned, according to this strategy document, that was approved by CERN Council, but not only CERN Council, but also by ministers of education and science from all member states. So there are 2 options. So as I mentioned, first option is the lepton collider, E plus E minus. So the plan is to make it real during the 4th decade of this century. So all this period is dedicated to the preparation, to the feasibility studies, but also R&D and so on and so on. And then implementation and operation of FCC E plus E minus is planned for this period, and the Hadron Collider version end of the century. So this is the plan for this feasibility study. We are working also. Okay, this is you know what was the main achievement for this FCC feasibility study. It was, and this I have to tell you that this was a very painful process to find where to place it in the region, because it's not so trivial, because we have a lot of constraints from accelerator symmetry point of view, that not everything can be put where we would like to, but certain things must be where they should be. And in particular, access to certain things also is needed. So just to put this underground with access from the surface, it was not easy, and also to respect all other constraints like geological and so on and so on. This was a very painful process, and about 100 different layout was considered, and each required very sophisticated simulations from accelerator design point of view. So this was completed. So now the preferred version is shown on this graph, and the total circumference of a tunnel, it's about 91 kilometers. So this is just an example of R&D that is ongoing towards. This is the beginning of the R&D towards development of equipment that will be needed for FCC lepton version, E plus E minus. So in parallel, we are working also on other options. So the options considered are so-called CLIC. CLIC is the linear collider, also this is lepton collider, but linear, and then you can see where it might fit in the region. And this is the position of the FCC. You can just compare how it looks like. So this option was already studied in the past, so we have a conceptual design, and this is feasible, and there is already part of R&D ongoing. But as I mentioned, this is not the preferred preferred option by physicists, by community. The higher potential is with FCC and two colliders. So we are also working on a muon collider version, but this is just started. But I have no time to talk about this, but this is a really challenging project. So let me switch briefly to research program. So first of all, I will start with main LHC experiments. We have 4 huge detectors that I installed in 4 places in LHC. This is ALICE, ATLAS, LHCb, and CMS. CMS and ATLAS are more or less general purpose detectors. They can observe everything. ALICE is dedicated to quark-gluon plasma studies, and LHCb it's dedicated to matter-antimatter studies in particle physics. So here you have a few numbers giving you the size of the collaborations. For example, ALICE, it's formed by 171 institutes from 41 countries. They have over 1,000 authors. This is the list of authors on their typical paper. So the Polish physicists are all participating in this, of course. The numbers are a bit smaller, but significant, because our particle physics community in Poland is of the order of a bit more than 300 people. So 90 of them are contributing to ALICE, coming from 4 institutes, 2 from Warsaw and 2 from Krakow. Atlas, it's a huge collaboration, as you can see, 250 institutes and close to 300 scientific authors. And from Poland, we have 2 institutes from Krakow and something like 76 physicists. The same for CMS. You have numbers and people also from Warsaw and from Świerk members, and LHCb also 3 institutes from Poland and 16 members. So this is how it looks like. Those are just a comment, because preparing this, I hesitated what should I put here. Those are what they claim, those are the scientific authors. But the all active members of the collaboration, like CMS, the number, it's approaching 6,000. So this starts to be something incredible. But among those 6,000, 2,340 are the scientific authors. So the rest are probably the technical and engineering. So I wanted to give you some highlights what was recently obtained by those experiments, but finally I decided not to do it. Why? Because this huge community is producing something. This is incredible. I calculated this. They are producing in average 1 paper per day. Those 4 experiments are publishing in journals 1 paper per day. And to make an overview, even for past months or even week, it's a challenge. So I can just tell you that they are really producing, and the main papers are now about the precision of measurements. So with accumulation of statistics, of course they improve the accuracy of what they measured. But also they are producing new results, like for example, what is a bit more relevant for Institute of Physics, new limits for monopole, for example. So this is main experiments on LHC, but this is not only this, because at CERN we have many more facilities, and I will just mention some of them. So the first complex, it's so-called, we call it super proton synchrotron North area. This is the complex of experiments that is using not LHC, but it's using super proton synchrotron, which you can just see here. Normally, this super proton synchrotron is just accelerating to its maximum energy, the protons, and injecting them to LHC. But it's doing this only twice a day for an hour. Rest of the time is just sending the protons to experiments that are installed in this area. And we have a number of experiments. I have no time to talk about all of them. I just selected one which is more relevant for Poland. So this example of experiment is so-called, we call it NA61 SHINE. This is the experiment that is investigating the production of kaons. This experiment, it's really, I have to say, dominated by Polish scientists, because for the total number of authors, which is 150, 64 are Polish. So Also, this is the head of this experiment. It's a Professor Gazdzicki. And this is in practice managed by Poland and also financed to large extent from grants. So this is one of the many experiments we have installed in this experimental hall. What they are doing and what they published recently, it was a quite interesting result. As I mentioned, they are specializing in production of kaons and looking into the statistics of this production. And what they discovered recently with very high precision that there is a symmetry breaking. So theories like a standard model are predicting that charge and neutral kaons in production like they are doing should be roughly equal, and that this discrepancy is very significant. So there is something wrong with theories, and this was demonstrated for the first time and presented last month for the first time in Houston during the conference. So you can see here, this is the plot showing any previous result in this field, but the precision-wise, this is order of magnitude more precise, and people are saying that now they are confident that there is something wrong with theories, and we will have to work on. So the next one facility, it's Isolde. This is a very specific facility that is working on nuclear physics, basically. So this is another facility that is using beams from this time from proton-synchrotron booster. And there is a number of small experiments that are installed in this hall, very many. I will just mention, I won't go into details because I'm exceeding the time. So just a few examples of experiments that that Polish contribution, the Polish scientists are leading. So I won't go into all details of this, but they are working on very many aspects related to many fields like medicine, but also astrophysics. Very nice experiments related to rapid neutron capture, and this is very important because this is the weak element of cosmology today, and refining the models in this is very important, and this is what they are contributing to. So this is another set of experiments that also is led by Polish scientists, and this is also very interesting. This is what they are claiming. It's really fantastic. This gamma MRI or beta detected NMR. What they are claiming, what sensitivity they can obtain, it's really fantastic. This is, for example, here they claim that as compared to classical NMR, they will have a 10 to the 9 higher sensitivity. Okay. Another facility, very briefly, with important Polish contribution is, we call it AD Elena facility, which is, I mentioned that we have 2 decelerators. We are not only accelerating, but also we have 2 machines that decelerate protons and produce antiprotons in this case. And those are the 2 machines. One is AD, which is the big one, that is just capturing protons from the P.A.S. and then decelerating this to MeV range, and then injecting to another small machine, which is called Elena, and this is decelerating further to 100 keV, and in this way we can do something with antiprotons in that case, and in particular, we can capture them and we can try to build anti-atoms. And this is what this facility is dedicated to study antimatter, basically either hydrogen, but also other. Just one example, this is the example from anti-hydrogen in alpha experiment. They are working for nearly 20 years. They obtained a very nice results, and recently they had a quite spectacular result. What this experiment was called Alpha G, and what they did, they built a cage in which they could trap a bunch of anti-hydrogen atoms, and then they were able to stop this trap and to observe for the first time whether anti-hydrogen will fall down or will fall up, how they call it. So this was done for the first time, and with a success. And this was a very nice experiment because first they simulated experimentally. They were keeping just anti-hydrogen in this trap, and with additional magnetic fields, they could really simulate acceleration of anti-hydrogen, which was polarized, of course, because this is the only way that you can trap it. And they applying extra magnetic fields, they could just apply some G from -3 to 3, and they could just simulate how annihilation will be seen after reaching the boundaries of this trap. So this was first done, and then there was the real experiment, and the real experiment is showing what many expected, but not all. Nobody was sure how this will work and how space-time is bended. But this demonstrated that it was falling down. Okay. So I'm coming to conclusion. So this is just a slide showing Polish involvement at various experiments at CERN. So I have to say that this is quite spectacular and quite visible. The Polish scientists are really visible, in particular in those facilities, smaller facilities. Smaller. This is not so small because we have hundreds of people or even thousands of people working there, but contribution is significant. But also the contribution to those giant collaborations like Atlas, CMS, and LHCb, it's also important and visible. Also, a lot of Polish theoretical physicists are collaborating with CERN. So this is our contribution is really significant. So, as a final remark, what I try to explain to you that we are working on within the accelerator complex, not only on what we have today, but we are preparing the upgrade, and we are thinking also about the future, and also a lot of effort is done in the development of accelerators for medicine. I had no time to do it, but we are doing this already for many years. So the CERN has an exciting and unique scientific program. I hope that I managed to convince you. We know that we have very many challenges, but also opportunities for discovering something new, and this is the place where national institutes and labs can really efficiently apply for participating, and as I demonstrated from Poland, we are really very successful, in particular for nuclear physics. We are very strong in nuclear physics. So also concerning the accelerators, as I shown that what we learned from LHC, we have to start thinking about the future very, very early. So today it looks like that I was involved in this a bit, but I was working even not for my children generation, but for the next one. Okay, that's all what I wanted to tell you. So sorry for a small extension of a time.
Thank you very much. Do we have quick questions that are pressing? We have a pressing quick question.
You mentioned initial the material science, which for us is interesting. Do I correctly remember that this means implantation of some Mossbauer active ions, or do you have some idea how it goes, this, material science?
This is what they are doing. I don't know all details, but it's exactly what they are doing. So they are just producing radioactive beams, in ions, and they just bombard materials, trying to implant what they are calling this. That they are implanting the foreign ions in the matrix of this material, and then they are just using those for various purposes. I mentioned the experiment that with this beta detected NMR. So this is exactly done in this way.
Okay, so I'm sorry, but we are running a little bit over time, so we'll have to finish up the questions. Let us thank Professor Šemko again.
Okay.
And all the speakers. And there's a last final word by the director of the Institute, Professor Pužňák.
So thank you very much for being here. It was a very long day. We have total 12 lectures, and so the summary will be very short to keep some balance between this, what was done today. Nevertheless, tomorrow there is also activity in this institute, but it is a rather open day. So I invite every of you, if you would like to come to institute and see how looks our laboratory. It will be possibility tomorrow. And concerning today, at least two people mentioned my name that I forced them to show some new results. Their sentences were true. I really forced them to show new results. The idea of this symposium was like this, that in total there were 12 lectures. First lectures, it was given by Professor Dietz, and it was just history of the Institute. So what was done in the Institute within 70 years. Next three lectures were just to show what is Institute doing now. So there was a theory, experiment, and some kind of innovation. However, such institution like the Institute, it is rather like bicycle. It cannot stay. It must move, because if it will stay, it will drop. So we need some kind of inspiration, what we should do in the future, or how we should think about our future. And therefore, we invited the 8 most prominent researchers to show and ask them to show what they are doing or what is most important for them. And this is just making this anniversary. We want to learn from somebody which are more experienced at what we should do in the future. So I hope it is fair, that because you contributed to us, but you are also know what is going here. So it is some kind of collaboration. Okay, I think that it is all what I want to say. Thank you very much for that you are here, and I am very happy that we have the possibility to meet so many people. We have in total about 130 guests, and they are everywhere. They are related to science, and not too often that we have a possibility to meet too many people together and just discuss about something which is related with activity of one institution like our institute. Okay, thank you very much. I would like to ask Professor Dewar if you want to say a few words.
Thank you. So I just have some organizational words to say. First, I'd like to thank all the organizers of this symposium, because quite a number of people have been involved in organizing this symposium, which lasted only one day, but there was a lot of work for this. And so I'd like to thank, I'm not sure how many of these people are here, but Anna Reshka, who was sort of in some ways heading the organizations, yes, thank you very much. And also dealing with the funding agency and things like this. And Alexander Vitlin, who was doing a lot of the organizing and planning of things, and Professor Bogdan Kowalski, and also Roman Puzniak and Magda Zowska-Kotor, the director and deputy director, because they were also involved quite a lot in planning how this should all play out. The IT department, Marek Barański here, Przemysław Iwanowski, and also Jacek Szczepkowski is not in the IT department, but they're in the back there. So thank you very much for making this all work nicely and smoothly. Magdalena Szymanek, who was our photographer, is she here or she's gone?